Hello, hello,
Hello, hello.
Yes, Sumit.
Yes, sir.
Are you checking the sound or what?
Sir, I am checking the sound. Just I connected one earphone. That's it.
Group. Dr. Goswami, everything's working?
Yes. Are you able to hear me?
Yeah. Good. Very good.
Yeah.
Thank you.
Okay. Thank you. Yeah. I think a keynote lecture is still going on, so it may take another 5 minutes or so. So after that we can start. So think a lot of participants are there already. So yeah. So our now speaker Professor Arindam Ghosh is there, so we can start the session. So good morning, all of you. Welcome to the conference Icee 2020. So my name is Dr. Ankur Goswami, and me and Professor Shamaresh Das is actually taking care of this particular symposium, 2D materials and devices. So today is the first session of the symposium. This session will have three eminent invited speakers across the globe: Professor Arindam Ghosh from Icee Bangalore Physics Department, Professor Saptarshi Das from Pennsylvania State University, and Professor Max C. Lemme from RWTH Aachen, Germany, followed by an oral presentation by Dr. Jyoti Jaiswal. And these sessions will be chaired by Professor B.R. Mehta, who is an eminent physicist and material scientist and Schlumberger Chair Professor from IIT Delhi. I think he does not need any introduction. He has been an outstanding scientist, and he has an extremely high contributions on experimental condensed matter physics. So he has been involved in various academic positions in various capacities. So now may I request Professor Mehta to take over this session chair and run this particular session. Thanks a lot, Professor Mehta. Yeah, you can now go on. Over to you.
Thank you. Thank you very much,
Yeah.
Professor Goswami.
Yeah.
So I'm very happy to be here and in the middle of four eminent speakers and many other participants. Welcome all of you. Good morning. So I think let's start the session because we are already slightly late, and I request all the invited speakers to restrict their lecture to about 25 minutes so that we have some 2 minutes for presentation. So I welcome the first invited speaker, Professor Arindam Ghosh, and he's going to speak on tunability of thermoelectricity in twisted bilayer graphene. And as all of us know, Professor Arindam Ghosh is a professor of physics at Indian Institute of Science in Bangalore, India. And his research interest involves understanding of physics and device concepts in multiple two-dimensional electron systems, with emphasis on transport, optical, and thermal properties of layered membrane. He has been recipient of several recognitions and fellowships, including Sorajanti Fellowship, Indo Science Fellowship in Technology, and Shanti Bhatnagar Prize, Oxford Instrument Young Nanoscience Scientist Award, and PK Memorial Award, and JC Bose National Fellowship. More, I think he is one of the best, most eminent scientists working in 2D materials, and looking forward to your presentation, Professor.
Okay. Can you hear me?
Yes. There's
Okay.
there's a little bit of noise. I request all the other participants to mute themselves so that there's no noise. Professor Ghosh. Yes.
Okay, I am sharing my screen. Just let me know if you are seeing it. Are you seeing the screen? Sorry, are you seeing the screen?
Yes, it is visible. It is visible.
Okay, actually there's a lot of echo from other side. If you others can mute it.
I request all the participants to mute themselves so that the noise is reduced. Please mute yourself.
Okay, there's still a lot of echo coming. Okay.
Professor Arindam Ghosh, you have two instruments connected together. So maybe one instrument, if you, that creates sometimes noise.
What do you mean by two instruments? I just have one laptop. If I go to the devices. Okay, am I audible now?
It is clear. Now it is clear.
Is it clear now?
Yes, now it is clear.
Okay, great. Okay, excellent. Just give me a buzz if you. Actually, you're right. I think it was my problem from my end. Sorry. So, okay, shall we get started then?
Yes, please.
Yes, please.
Okay, good. Okay, first of all, I would like to thank the ICE organizers for this opportunity. And this is I got slightly delayed because I was listening to the exciting talk by Professor Stuart Parkin, and it's amazing to see the kind of developments happening in magnetics. But I'm going to talk about something completely different. It's on twisted bilayer graphene, which is another direction of very exciting global research at this point. Very quickly, as I have given 25 minutes, I'm going to quickly acknowledge the people who have really worked on this topic. You can see 4 of the members of my group who are on the left, students and postdocs who did all the work actually, and my collaborators on the right. Most of the work that I'm going to show are already either published or will be published very soon. And the funding came from the Department of Science and Technology. Okay, so as such, twisted bilayer graphene is probably not of a great mystery anymore to anybody. We know that if you put one layer of graphene on the other, you create a super lattice, or what you call a Moiré lattice. And because the Moiré lattice is much larger than the intrinsic graphene lattice itself, its Brenner zone is significantly smaller. As a result, what happens, there is a lot of bands which starts folding on top of each other and giving rise to new electronic phenomena. And this has been of great interest of late. You can see you can achieve different ranges of physical properties by making the angle very different. For example, if you take 9.43, this was a calculation nearly 9 years ago, and you can see that for large angles, you really do not have much different. Two graphene layers essentially are decoupled from each other, and you preserve. Let me just switch my pointer on so that you can see it. Yeah, so you can see that we have nearly conical structure of the graphene maintained. So two graphene layers are essentially decoupled. Whereas if you look at the lower angles, which is in the order of 1 point. Yeah, is there a question or anything, or am I audible? Okay, I'm hoping that I'm audible.
Yeah, please go ahead.
Yeah, great. So if you go to lower angles, you can see that the two graphene layers have now started getting hybridized and leading to very interesting flat electronic bands, and the flat electronic bands usually lead to a physics of strong correlation. But it's not just the electronic correlation that's of importance. What happens is in even the lattice vibrations, when you create these twisted bilayer systems, they get hybridized and correlated between two layers. As a result, for example, if you take this twisted bilayer graphene with two layers which are separated by about 0.3, 0.4 nanometer distance, you get the out-of-plane vibrations of the two lattice create new Raman modes. For example, this is a ZO Raman mode, which is out, breathing, or we call it breathing modes, which are pi phase difference. Two layers are essentially, vibrating in opposite phase. This can be immediately checked with Raman spectroscopy. These are the Raman spectra for these vibrational modes, which have come because of the coupling between the two layers. Typically, these Raman modes are in the order of 100 centimeter inverse or 100K Kelvin or so. That's the energy. Okay, so what I'm going to talk about today is how do you combine the electrical transport and thermoelectricity to look at the phenomenology of the twisted bilayer systems in a new way. And by that, I will use twisted bilayer graphene to both first, the top emphasis will be to look at the nature of the interlayer coupling. And for that, we will look at the thermoelectricity across the two planes, which are creating the two layers. Okay? Which means that I will look at the thermoelectric property at really distances in the orders of few angstroms, or 2 or 3, 0.2 or 0.3, or 0.4 or 0.5 nanometer. So that really forms the shortest thermoelectric, that is available. However, what's important about thermoelectricity is that it is also very sensitive to very low energy structures in the density of states. So you can look at the electronic phenomena and also strong correlation effects. These two actually will look at the thermoelectricity in the plane of the two-dimensional twisted bilayer graphene. I will just give you some examples, but unfortunately with the time, I don't think I'll be able to go very deeply in the third topic of strong correlation effects, close to the magic angle, where people have looked at very interesting electronic phenomena. Very quick primer on the thermoelectric and electricity and Seebeck effect. You have a solid, and if you create a difference in temperature from one end to the other, you create a voltage. And this voltage, ratio of voltage and temperature gradient, gives you the thermoelectric power, or Seebeck coefficient. This has got two components. Usually one's a diffusion component, which is created by just the impurity scattering and photon scattering as well, but assuming they are static. And then you have these within the relaxation time approximation, the standard Boltzmann relaxation, Boltzmann transport semi-classical formalism. You have this Mott formula, which is extremely important, and we will be using right through our talk today, which is essentially the derivative of log of conductance with respect to energy. It's just a question of reorganizing these parameters. What's important here is that the fact that thermoelectric power is derivative of logarithm of conductance with energy makes it extremely sensitive to any form of Moon effect or any structure in the density of states. And this can also be experimentally verified. You can just take this as Mott and split this term of the d log GdE in two parts. And one is experimental part, which is this is directly obtained from experiments, which n is the density. We have field effect transistor geometries from where we can get this term. And this gives you the information of the density of states. In addition to this, there is another component of thermoelectric power, which comes from the phonon drag, where you have got a large number of phonons, and because there's a difference between the phonon number from the hot end to the cold end, the phonons will also be moving, and when they move, they will drag the electrons along with them. And as a result, there's an additional voltage that comes up. And this phonon drag contribution of thermopower is now directly coupled to the phonon occupation number, and hence you should be able to get phonon energy and Bose-Einstein distribution, as well as electron-phonon coupling in your system. Okay, so with this, let me just try to tell you, let me show you, what experimentally we normally do. We take a in-plane, if I want to look at the density of states, that means in-plane thermopower, for example, and as an example, I took bilayer graphene. You take a bilayer graphene, make these contacts, you pass a current, and you create a temperature gradient, and when you measure the voltage, that gives you the thermal voltage. That's simple. Experimentally, this is the resistance of this bilayer graphene between these two contacts as a function of the gate voltage. You can see the resistance shows this nice bell-shaped behavior. If I measure the thermal voltage by passing a heating current here, you see this is something which looks like this, almost like a derivative of this equation, this experimental data. And as a matter of fact, if I use the Mott formula and I take this dg log n from the experiment that we have done, and use dn de from the fact that the bilayer graphene is nothing but a standard two-dimensional system with free electrons, and then your density of state is constant, then we can actually calculate and find that these two are matching very well, which essentially means that the standard bilayer graphene at zero gap will be nothing but a classical semi-classical Boltzmann equation, and thermoelectricity can come up through that itself. Okay. However, I will give you a little bit of insight into that, and this is something which Aditya and others did. So we take a bilayer graphene and we find that the thermoelectricity is extremely sensitive to the right band dispersion relation that you use. For example, in this data, this is the same bilayer graphene data. We have used, instead of a bilayer graphene, if you use the density of states of a single layer graphene, you can see the red one, the single layer graphene, it simply doesn't fit. It's only when you use bilayer graphene, it starts fitting the experimental data, which is great because we know how sensitive we are to the use of the real density of states. An even deeper thing comes up, and this is Aditya's experiment. I'll go very quickly through this. Suppose you create a gap in bilayer. This gap can be put by applying an electric field across the two planes. And for example, when you have a gap, then you have, this is your resistance versus gate voltage behavior. However, when you open this is without a gap, and when you open a gap, resistance versus gate voltage actually shows very high resistance at Dirac point. That's because Dirac point has a gap now. Now the thing is, there is nothing in terms of the features on these regions, on this resistivity. So once, if you do a standard thermoelectric measurement on a gapped bilayer graphene, you should be able to simply see the derivative that I showed earlier. But it turns out that's not to be the case. For example, this is the experiment of Seebeck coefficient on bilayer graphene, and you can see that there are regions here which clearly differ from this, and which is highly repeatable in various gaps. You can see these additional shoulders that are coming up, and that leads to an apparent violation of the Mott relation. What Aditya figured out is that that is not the case, and you can actually understand those additional kinks and in bilayer graphene from a simple framework of the trigonal warping and Lipschitz transition. Remember, these bilayer graphene are extremely high mobility, so their charge inhomogeneity scale is much smaller than the energy scale of the Lipschitz transition. What happens is that because of the Lipschitz transition, of course, there are a little bit more detail here, but I will not go into that because of time. But there is additional Van't singularity at a small energy. And that comes because of the next nearest neighbor interaction between bilayer graphene across the plane. This is a skew hopping parameter gamma 3. If you take that into account, then these kind of these shoulders that we see in experiments, that can be explained very nicely. Of course, there are details here because this is at a high gap, so there are other effects that cannot be taken into account through simplistic modeling. But importantly, this part, the shoulder part, can be explained quite nicely by looking at bilayer graphene trigonal warping and Lipschitz transition, which gives us a new way of looking at low energy density of states, and that's what I wanted to talk about. Okay, so what happens to the cross-plane coupling? So our goal here in this talk is essentially to look at the Seebeck coefficient across the two planes, to look at to ask the question whether we can track the coupling of the two layers in a twisted bilayer graphene system. First, very quickly about the very large angles. When you have large angles, you do not really expect the two graphene layers to couple. And in these cases, the way we do the experiment is that if our intended angle is theta, we give it an additional 60-degree angle so that we can access the two layers nicely. We pass a current in one of the layers and measure the voltage between the other two so that we can measure the thermoelectric voltage between the two layers. And we have a gate on top so that we can vary the electron density or the hole density in the overlap region between the two layers. This is a typical device. It looks very nice. And usually we encapsulate the two layers by boron nitride to get very high mobility. To give you data, this is a typical R versus VG of the region which is underneath, and this is a cross-plane transpo in which you pass a current from this layer to upper layer and measure the voltage between the two layers that develops. Okay? And if I look at the heating result, that means the thermoelectric figure of merit or voltage, you can see the current now is entirely within the top layer and the voltage is still between the upper and lower layer. With higher voltage, you can see the thermoelectric figure of voltage is increasing. And if I divide the thermoelectric voltage by the square of the current, which means it is coming from the heating, then you can see all the thermoelectric characteristics collapse, showing that this is because of the heating alone. But the problem is that we can see that there is very little, the Mott formula does not seem to explain the observed experimental data. And we realize the reason behind it is that it is not the diffusion thermopower that is dominating the observation, it's actually a phonon drag. To give you the physical picture, if you have got two layers of graphene, one at the top and at the bottom, one is hot, other is cold, you have got larger number of phonons that actually kick the electrons out from the top to the bottom, and that leads to the voltage, the Seebeck voltage. And as a result, if I do very simple back of the envelope calculations, you get delta V over delta T to be directly proportional to the derivative of the phonon occupation number with respect to temperature. And all these lines that you see in the experimental temperature dependence is nothing but this equation, which also gives us very nicely the energy of the phonons which are responsible for this thermoelectric voltage. And it turns out that this phonons are nothing but those out-of-plane breathing modes, which are giving exactly the same energy that we like to that we see in the experiments. Why? But what happens if you go down below at a lower angle between the two between the two layers? And again, we give a 60-degree plus the theta. Now, but the theta is less than 2. We see now we are actually dividing the thermoelectric voltage. That means, which is Mott formula. These are the experimental data, and these are Mott. The black one is the Mott calculation from the observed resistance versus temperature. Also, resistance versus gate voltage. I'm sorry, but also the thermopower is directly proportional to the temperature, and you can see the linearity, which again is the direct characteristics of the Mott formula itself. Okay, so what is the overall picture now that is emerging in these, our experiments is we have got theta, which is when the angle between the two layers is larger than 5 degrees, we seem to be determined by the electron-phonon coupling and out-of-plane phonon contribution to thermopower, whereas when the theta is less than 5 degrees, we are picking up the Mott formula. Around that region of 5 degrees seems to be the transition from one mechanism to the other. We can now understand that, or at least attempted understanding that, and this depends, based on a calculation done, nearly 10 years ago by McDonald and group, on simply the hopping probability of electron from one layer to the other. And if you see the overall hopping rate, you can see that below about 5-6 degrees, where the phonon frequency becomes equal to the hopping rate of electron from one layer to the other, which means if you are lower than 5-6 degrees, you will be determined primarily by the electrons hopping from one layer to the other. Whereas if you are at larger angle, which is larger than 5 to 6 degrees, it will be phonons which are far more effective in making the electrons make a transition from one layer to the other. So that's actually came out to be very nice. Okay, so this is the overall picture. Low angle, it is electron hopping, and whereas higher angle, it is the phonon mediated hopping. Those who are applied oriented here, I can show you some very interesting outcome of these experiments. You can see the power factor of these, twisted bilayer graphene. If I take an effective number, it can actually probably lead to a very interesting new thermoelectric. But we are now looking at the thermal conductivity between two layers to see what kind of thermoelectric figure of merit that twisted bilayer graphene can give us. Okay, in last couple of minutes or so, I'm going to give you a very short glimpse of what's happening in the twisted bilayer graphene when the two graphene layers are aligned within close to that magic angle where electronic correlation becomes important. Remember, I'm going to show what happens at the close magic angle, not exactly at the magic angle, which is also happening. But this will at least give you that the fundamental directions that we are taking. Again, the devices here are made in two ways. One, the way I already have told you, where the two layers are given a 60-degree additional twist. But in addition to that, we have made the graphene with the standard tear and stack method, in which what you do is that you take the graphene layer and use a layer of boron nitride to simply cut it in half. And you can see this is the boron nitride, this is graphene. And by using the boron nitride, you just cut the graphene in half, and then you lay the graphene on the part which was originally uncut or sitting on the silicon oxide by giving it a small twist. So I don't know whether it is possible for you to view this, but there is a very tiny twist. You take up this particular layer out of the graphene, original graphene, and put it back on top of this with a small twist. So you know exactly what the twist angle is. And eventually the device looks like this. You can see this is a single layer region which was extending. So if I go back, we always, for thermoelectric measurement, we always keep an additional region which is protruding out of the twisted bilayer, which can be used later for heater. So this region is the single layer graphene, and this part is the twisted bilayer. So this is the twisted bilayer which is gated from both bottom and top, whereas this is the layer which is extended single layer region, which is by passing a current through this, you can use it as a heater. So what happens in these kind of systems, when what heater that I'm going to show you is about 1.6 degrees, this calculation was done by Manish Jain and his group. You will see that there are three regions where the density of states go to zero. The region where the original Dirac point, and also when the Moiré lattice is completely filled, this is Moiré band, the lowest energy Moiré band. Okay? So these are the first. So these are the regions where there will be resistance peaks. And as a matter of fact, this is what we see. On the left, what you see here is the resistance is peaking at 3 points, and this is the complete filling of the Moiré cells, and this is the Dirac point. This is half filling at the bottom. This is half filling of the Moiré cell. Now, if you do a temperature dependence, you will see the resistance versus temperature in these two regions are linear completely, and which was another reason why it was quite exciting, because when original paper on the superconductivity came out, it was connected to the high temperature superconductivity, because in these regions, the resistance versus temperature was supposed to be linear, and that's supposed to tell you that there is a possible non-thermoliquid behavior, and the metal is a very strange metal and not something that is conventional to standard our solids that we see. So I'm going to give you a very quick example of the data that we are getting here. I'm almost done. So if we look at the resistance, I would like you to concentrate here, and you'll see that here the derivative will tell you that it cannot be, this should be zero, and we do see zero at half fillings. And that means at high temperature, it is a Mott formula. Then as you lower the temperature, you can start seeing that there's an additional component that develops at the regions of the half filling. And 20 Kelvin, you can see additional, there is a significant enhancement. It is no longer zero, the thermoelectric voltage, even though R versus Vg, which if you take a derivative, it will show you zero. And if you go to 10 Kelvin, you can clearly see that there is an additional negative component here and additional positive component here. And this is a 3 Kelvin, you can clearly see that this is an excess thermopower. Now, if I take the Mott formula, then the pink one is the Mott formula calculation, and you can see it explains, the Mott formula can explain the thermoelectric voltage at almost all gate voltages, except when the Moiré lattice is half filled, this region and this region. So these are excess thermopowers. It turns out that these excess thermopower are independent of parallel magnetic field, and probably there is a possibility of new orbital entropy that is coming into picture. I'm done. So this is my summary. We see thermoelectricity as an emerging probe to the diverse phenomenology of twisted bilayer graphene. We have shown that around 5 degrees there's a transition in the dominant force that makes thermoelectricity become electron dominated at lower, and the hybridization between the two layers start. And whereas at higher angle, at larger than 5 degrees, it's the phonons that contribute to the thermoelectricity most. And thermoelectricity can be easily shown to be sensitive, extremely low energy features, which resistance versus gate voltage simply doesn't give you. Okay, and hopefully we will come up with new results on the anomalous thermoelectric contribution at half filling when you go closer to the magic. With that, I would like to thank for your time and attention.
So thank you, Professor Ghosh, for a very nice and stimulating lecture. And any questions, participants? We have some time for questions.
Ask a question. Am I audible?
Yes, please.
Yeah.
Hey, Arindam, extremely very nice talk, actually. I mean, I learned a lot. So I have a kind of a quick question about, what kind of a temperature difference do you think that can exist between these two, twisted bilayers of graphene? I mean, when you calculate the Seebeck coefficient, I mean, do you need that information?
Yes, absolutely. So Shantuji, thanks very much. Good to see you. First of all, yes, and that's a great question because I didn't say much about it, but it's amazing, particularly when you are looking at high twist angles of 12, 13 degrees. We calculate the delta T, the difference in temperature, by using the resistance of the two layers as thermometers, okay? Because you just measure this resistance. And the number is amazing, it's staggering, it's about 30 Kelvin. So it can be even more. So I'll just quickly tell you that actually that figure is there, but I didn't unfortunately get time to see anything. Here, if you look at I don't know whether you can see the slide. This is delta T calculated.
Slide, yeah.
So you can see that delta T can go up to 20 to 30 Kelvin.
I see.
And think about the fact that there are just 0.3 nanometer distance between the two layers, and you are maintaining a temperature difference of 30 Kelvin. It's staggering.
It is. It is. Yeah. Wow. So do you think that this effect is going to be very similar to other 2D materials, or is it very unique to graphene?
I think it should be similar. The graphene is easiest to measure because of all the advantages you have, and the problem of the electrical conduction within the plane. Other 2D materials means essentially you're talking about, say, MOS2 or others. There, in principle, it's possible, but it's probably a little bit more challenging because the electrical transport is relatively more semiconductor-like there. But in principle, it should be very similar.
Right. Okay, great. Yeah, thanks.
Yeah.
Mr. Bose, I have a small question.
Yeah, please.
Yeah. So in the system where the angle is 60 degree or different angle. Yeah. Does it make that in which direction the current flows, or it's not important?
No, I mean the 60 degrees is what we do to maintain the symmetry of the lattice. That means if I want theta to be the misorientation between the two layers, I give 60 plus theta, so that effectively the two lattices are separated by theta, because of the 60 degree symmetry of the graphene lattice itself. The current essentially is always sent from. When you're looking at the top. The cross-plane thermoelectricity between upper and lower layer, it is always in that upper layer, and you measure the voltage between upper and lower. Or you can reverse the process as well.
If you reverse it, no difference in the voltage.
No, that's the whole point. Yes, that's Onsager reciprocity that you have to cross-check. Absolutely. That's a great question.
And maybe can you tell, because thermal conductivity is another very important property which has to be measured, and you mentioned it.
Yes.
So can you give some your reflections on the difficulties in measuring thermal conductivity in a 2D material?
You are looking through the projects that we are going on in the group. So you can see the very interesting part. That is, if you look at this calculation that was done nearly 9 years ago now, the thermal conductivity between two layers is expected to be very, very small. The simple reason behind it is that the number of phonons are much lower now. As a result, one expects an extremely high ZT factor. However, that said, one has to be careful about it, because we now have this hybridization of phonons between the two layers, which can increase the thermal conductivity significantly. But this is the problem. The measuring thermal conductivity across two layers, which are 0.3 nanometer away, is a very difficult task. So we are up to it now. We have some ideas about how to get this done by looking at very, very carefully engineered heat flow. That is the biggest challenge. That the heat flow must be contained within the overlap region between the upper and lower layer. And that is extremely difficult. And you have to calculate the heat flow. For thermal conductivity, you need to know what the heat flow is. Just measuring the two temperatures are not enough. And that is where the challenge is, but I think we should be able to get something very soon. But if I simply take these numbers from calculations, it actually comes out to be massive. It comes out to more than 3 at room temperature, which can be a revolutionary thing.
All right. So I think if there's any other question, then we have time for a small question. I think
we're not audible actually, Professor. Yeah.
All right. So we thank Professor Arindam Ghosh for a very nice presentation.
Professor Mehta, Professor Vasily has a question. He is not audible, I
Please.
guess.
Oh,
Yeah, please
hi,
ask.
Vasily. Oh, good to hear.
Yeah.
Please ask, or you can message the question if you want.
Okay, sorry, can you hear me?
Yeah, Vasily, I can hear you. How are you?
Hi, sorry for I messed it up. So it's a very nice talk. I wanted to comment on the intellect transport. We did the calculations back in 2013 when you add a phonon, this intellect phonon out of plane, and it gives electrical transport across the layers. And what you mentioned here about the phonon drag, essentially the same Hamiltonian can give rise to the effect you are discussing.
Exactly. Right. So, Vasily, this is the expression I took from your paper with Fedon. And, this, and we calculated essentially by taking the KF to 0, you can see this extension or extrapolation to 0, it exactly matches the number of 100 Kelvin or so of the out of plane phonons. And that comes out by fitting all these, if you fit these thermoelectric lines, thermoelectricity voltage versus temperature, by looking at the derivative of the occupation number, you get exactly those phonons.
Oh, but what about twisted Bali? If it's 100 wave 100 wave numbers when you are AB stack, but once you twist it, other people have done the calculations. This omega gamma becomes much lower.
Yeah, well, I mean, if you look at the calculations, this is essentially the calculation. I don't know whether you can see my cursor. This is the calculation. And you can see the ZO1, and this is the difference in the Q vectors at 12 to 13 degree angles, the delta K theta. And this is essentially, I will have to check the other calculations that you mentioned, but I thought this is the calculation which gives you the energy of the out of plane phonons.
For AB, okay, so, okay, good. Yes, sorry. For out of plane, yes, but the shear mode would be.
No. Shear modes is different. This is out of plane breathing modes.
Good. Sorry. Thank you.
Thank you very much. Thank you very much again, Professor Ghosh. Very nice presentation.
Thank you. I'll stop sharing.
Yeah. So we go now to the second presentation, second invite to talk. And the title of the talk is Novel Devices for Biomimetic Sensing and Computing, which will be presented by Professor Saptarshi Das from Millennium Science Complex University in USA. Professor Das is working as an assistant professor at Engineering, Science and Mechanics and member of Materials Research Institute and College Graduate Degree Program at State. He's there in this position since 2016. And he's the recipient of Young Investigator Award from United States Air Force Office for research in 2017. The research group is a new multidisciplinary area of science, namely biomimetic sensing and neuromorphic computing and related applications. So, Professor Das, we welcome you to this conference, and we are looking forward to your presentation. Professor Das, please.
Yeah, thank you, Professor Mehta. And am I audible?
Yes, please.
Okay, great. So yeah, again, thanks for the invitation. And I think now I will take you in a very different direction compared to what Arindam was talking about. This will be much more applied compared to the fundamental science that he is exploring. So what we are trying to do in our group is essentially trying to develop different sensors and computing primitives using these 2D materials. Just to kind of give you a brief motivation behind using this 2D material for computing is the fact that our essential computing power has been increasing over the last few decades. In fact, if you think about today's supercomputer, it is as good as a single human brain, and within next 10 years, we'll be essentially reaching the computing power, which is kind of the entire humanity combined. But there's a problem. I mean, these supercomputers are extremely energy inefficient because they consume huge amount of power, close to like 10 megawatts, and they're pretty big compared to the human brain, which is actually very small compared to the size of a supercomputer, and also is extremely energy efficient, almost like 6 orders of magnitude. Now, the primary difference between the way the brain performs computation and the computers do its computation is lies in this fact that von Neumann, developed this idea of separating the logic and the memory unit from each other. And therefore, your computation happens in the central processing unit while all the data is stored in the memory. And whenever you shuttle the data between the memory and logic, you actually consume a lot of energy. And in principle, this is avoided in the brain by kind of using a non-Neumann architecture where the neurons, which are the computing elements of the brain, are right next to another neuron, and all the memory is stored in the synapses, the chemical synapses, which essentially connects the two neurons. And you can see that in an adult human brain, you can find up to 100 billion neurons. Each neuron on average is connected 1,000 other neurons. So essentially, there are like 100 trillion synapses compared to, kind of a billion transistors on a microprocessor chip. So brain is amazingly powerful in terms of the computation. And there are a few other aspects of brain which are also important, is that brain is analog in nature compared to a digital computer, and brain does computation in a probabilistic or stochastic approach compared to a deterministic approach taken by the modern day digital computer. Now, essentially, if we really want to harness the power of human brain in computation, we essentially have to devise, chips which are much more smarter compared to the current day technology. And this is exactly why there's been a lot of progress in artificial neural network. I think many of you have probably heard about it, where you essentially kind of capture the basic primitives of the brain, which is the neurons, which are this the circles, and then the synapses are the connection between those neurons, which are typically used to store, memory or the weights. Now, there has been a lot of progress in the neural network. We have like deep neural network every day in our life. We are actually kind of using these deep neural network whenever we open an app in our phone, or we do a Google search. I mean, there is always this deep neural network which is behind the back. In fact, all semiconductor industries are actually working a lot in making this artificial neural network. There's a lot of new chips that have come across, but they're all based on the current silicon CMOS technology. And we all know that this CMOS technology is kind of ending, nearing an end because of fundamental limitations at the device level, because of the Boltzmann statistics, which doesn't allow the energy of the MOSFETs to go down any further. There's a quantum limit which doesn't allow silicon to be any more thin. It kind of has an exploding band gap, and it doesn't really remain a semiconductor at that stage when you try to make it extremely thin, which essentially kind of boils down to the fact that we cannot make the transistor any smaller. And at the same time, the complexity scaling has also stopped because of this von Neumann limit. I mean, the processing power is still going on because we are simply putting many of them together instead of making one of them, much more computational heavy. And this is exactly what we need, is an innovation in materials, devices, and in architectures in order to combat the energy and area bottleneck of the current technology and try to make it much more efficient. So here is exactly why the 2D materials are getting a lot of attention, is that they are ultra thin. As Arindam mentioned, graphene, a monolayer of graphene is like 0.3 nanometer, while HBN, MOS2 are a little bit, MOS2 is like 0.6 nanometer, but they're actually almost like a factor of 10 smaller than the current silicon FinFET technology. And if you do a back of the envelope calculation using this kind of a scale length, you can see that the silicon FinFET technology cannot be scaled, beyond like 3 times this lambda value, which is 14 or 10 nanometer, while the 2D FETs can be scaled much further. So the scaling problem can be solved. But the scaling is not the only problem. As I mentioned, novel devices are going to be very important. So here, essentially, what we realized very recently, we kind of published this paper on graphene-based memristive synapses. We have all heard about memristors using oxide semiconductors, but this is kind of the first time we demonstrated, graphene can also be used as a memristive structure. And we show that the similar kind of a forming and setting process can happen in a graphene-based device, in a graphene field effect transistor, just by applying very large drain biases. And the origin of the memristive property of graphene has to do a little bit to this interface of graphene and the alumina backgate oxide that we are putting. water molecules get captured in this interface because of the graphene transfer process, and these water molecules can actually have either an associative or a molecular adsorption, which is essentially the reason for this memory strip property in graphene. Essentially, the water dipoles change their orientation in a simple layman term, and that essentially induces different amount of charge in graphene, and that is why we can essentially program it into multiple different states. So here you can see that by applying different programming voltages, I can change the programming state of the graphene, and I could also apply a reset pulse to again get back to my initial state. And here you can see that the Dirac point of the graphene can be changed using programming, and then it can be again revert back by the resetting process. So the graphene can be used as a memristor, but what is very unique about a graphene memristor compared to the oxide-based memristor is that it is much more analog in nature, which means that I can attain any state in graphene, because in a conventional memristor, you have a high resistance state and a low resistance state. But here, as I show you, that I could attain 2, 4, 8, 16, in fact, any number of states. Of course, if I go to large number of states, the precision of the states actually tries to kind of get minimized a little bit. And that is always true for analog memory. If you want to have more number of states, your memory ratio is going to be impacted to a certain extent. And as you can see that I could actually do a programming, and again, I could be a reset batch. You can see a staircase downward and a staircase upward. We show that I can have a weight update in my graphene synapses the way I want. And the advantage of that is that I could actually use it in a neural network for vector matrix multiplication or the VMM operation. And because neural networks actually uses a lot of different weights, and these weights has to be ultimately implemented in a hardware. When you implement it in a hardware, you have got only finite number of states because of the memory strip, other memory strips around there. So essentially, you have to quantize these weights to their nearest numbers. Now you can see that once you do that, you have actually a lot of error in the hardware calculation. In a software, you can anyway, but when you implement it in hardware, you actually essentially get a lot of error depending upon how your weights in a neural network is distributed. However, if you use a different kind of a weight clustering scheme, which we call the K-means clustering, this is only allowable for graphene memristor because we could actually precisely choose a state. You can clearly see that the error can be very drastically reduced, and this is exactly what we demonstrated using a kind of an experimental prototype device. It's a very 2x2 memory strip array, but we can clearly see that the error for this uniform quantization is much higher compared to the K-means clustering. So that is what the graphene memory strip property could be utilized for high precision neuromorphic computing. Moving on, we also realized another different type of synapse, which is called the Gaussian synapse. And this is something I have also presented, I think, in the previous Icee. So I will not go into the detail of that. This paper is now published. But here we are actually using two different 2D materials. One is MOS2 and the other is black phosphorus. And we can actually create a device, the IV characteristics of which looks like this Gaussian. And the idea of using a Gaussian device is essentially the fact that we could actually then inculcate probabilistic computing compared to the typical deterministic computing that is still going on in the artificial neural network. A PNN actually allows you to do unsupervised learning, for example, a regression kind of analysis where you do not really know how your data has to be fitted. You have to have a prior knowledge of what kind of a fitting I'm going to use, a linear or a parabolic. That's a prior knowledge you need to have. But if you do not have that prior knowledge, you cannot really do a regression fitting. But using a Gaussian mixture model, you can actually do this fitting without having any prior knowledge. So essentially, we could create unsupervised learning using these Gaussian synapses. So now moving on a little bit, so I talked about computing, but computing is not the only thing that we are looking into, because right now, I mean, you think about the era that we're living in is called the Internet of Things, and the Internet of Things is all about different kinds of sensors, which doesn't need to be smart enough, but it also needs to sense the environment around and essentially communicate among each other. Now, if you think about the sensing part, I mean, and we know that the 2D materials could be used as sensors because of their large surface to volume ratio. But then we actually look into a little bit different type of sensing. I mean, we have a lot of solid state sensors, but one thing that we typically ignore is the fact that, there are lots of animals out there which actually perform, sensing operation way better than we human can do. In fact, octopuses have polarized vision. The spiders can essentially detect micro vibration. These African bush elephants can detect water from almost 50 miles distance. The catfish is an amazing sense of taste, and the barn owl can hunt in complete darkness. So there are actually animals out there which can do even better than the 5 senses that we have. For example, jewel beetle can sense infrared radiation, and bees can actually sense Earth's magnetic field. And their precision is actually way better than, in some cases, the best sensors that we have got today. And what is even more fascinating is that they do all this at a very, very minuscule energy expenditure, because they really have a very tiny brain. And using special neurobiological architecture, they are able to solve this kind of a sensory problem in a very unique way. So I'm going to give you like 3 examples. The first example is this barn owl, which can essentially hunt in complete darkness, which means that it can localize sound with an amazing precision of 1 to 3 degrees. And sound localization is actually a very tricky problem for any mammals. And the way we do it is by looking into the time difference between the 2 waves that arrives at the 2 ears, because depending upon which direction the sound is coming from, there will be a time difference between the sound arising at the 2 head. Now, depending upon the head size of the animal, this time difference could range from hundreds of microseconds to a millisecond. But the problem is the brain, the neurons can fire only every few milliseconds. So therefore, we are trying to solve a computational problem which is in the microsecond domain using computational primitives which are in, operating in milliseconds. So that's a very tough computational problem. And the way it is solved in the barn owl is by converting this temporal coding into a spatial map. And the way it does it, it uses 2 types of neuron. One is called the coincidence neuron, which essentially detect a signal when it arrives at that neuron, at the same time from the top and the bottom. And the other one is a delay neuron. So let me give you a quick cartoon, and a video of how it is actually done. So if you can see the video, so let's say a sound source is coming directly from the front. So it reaches both the ears at the same time. So it propagates to the delay neurons and coincides at the middle. But if the sound is coming from the left side, then it reaches the left ear first and it starts propagating. It reaches the right ear later. So the coincidence happens at a different position. So just by knowing where the coincidence took place, the barn owl is able to figure out which direction the sound is coming from. And this is exactly what is done in this unique neurobiological architecture inside the barn owl. And this is something we try to mimic using our 2D devices. So we actually use a split-gated transistor, where instead of using a full gate, we use a split gate. So that whenever both the gates are actually at high voltages, I can actually turn on or turn off the channel of the transistor instead of a single gate. So this device acts like a coincidence neuron. Then I have some delay circuit, which is simply RC circuits, and then we combine both in order to make this neural architecture. So here is the optical image of the device, a closed look of this map of these different split gates, which kind of ranges from a range of 200 nanometer to 600 nanometer spacing. And this is a cartoon of the device. And here is the device characteristic. And you can clearly see that based on the split gate spacing, the device characteristics is different. So what this device is essentially doing is that in the vertical direction, it is actually doing a computation which is digital, which is essentially coincidence. When both inputs are high, the output also is high. But in the horizontal direction, it is actually doing an analog computation. So we have a device now which can do both digital and analog computation and create a map of this, the sound profile that is coming from the surrounding. And what is the accomplishment is that, okay, the barn owl can localize sound in 3 to 6 degree precision, but by using a nanoscale device, our precision could be actually way better than the barn owl. So essentially, we are learning from nature and essentially trying to, beat it to a certain extent and becoming, much more precise. So the second example that I'm going to give is actually another insect. I mean, it's a locust, and we all know that maybe like 2 or 3 months back, the locusts were creating wide-scale devastation in agricultural fields. So they're actually very notoriously known in order to create a lot of damage in agriculture. But then, what is very unique about the locust is that they fly in swarms, which has almost like millions of locusts, and they fly all together in all random direction. But the rate of collision among them is very, very low. So they are amazing collision detectors, and collision detectors are going to be extremely important when we talk about autonomous vehicles and autonomous drones, which will be monitoring different kinds of activities in the near future. So what is very amazing about this locust is that it uses a single neuron, which is called this lobular giant movement detector neuron, or LGMD neuron, in order to detect this collision. It doesn't even require a complete brain. Just a single neuron can actually perform this difficult computational task of collision detection. So what it does when an object approaches the eye of the locust, there are 2 stimulus. One is the angle of projection, which is theta, and the other is how the angle of projection changes, which is the angular velocity. Now, what the locus does is it takes this angular velocity and creates an excitatory response using a neural pathway, which has these photodetectors and these different layers of the neural pathway in the locus eye. It creates an excitatory response. So as the angle increases, the angular velocity increases, the neural response also increases, while the angular projection, it actually inverts it and creates an inhibitory response. So using some feedback mechanism. Now you can see that by combining the two responses, it creates a non-monotonic firing rate. And the firing rate actually peaks just before the collision. And then the locust actually flies away or escapes the collision. So it's a very unique mechanism. So we thought, can we capture this kind of a mechanism using a device? Now, there has been other vision chips which have been developed in the past in order to essentially capture the LGMD neuron, but they have been using 34 transistor, 5 capacitors, and they're pretty big compared to the neuron. What we did is we actually used a single MOS2 transistor in order to kind of mimic the LGMD functionality. And the way we did it is that we used the optical property of MOS2 in order to create the excitatory response in an MOS2 photodetector. And then we use a stack, which is essentially a programmable memory stack. It's kind of like an FPGA kind of a structure, a flash memory, where you can actually program it to program the MOS2 in different states. And by using it, we were able to capture this response. So let's see this experimental demonstration. So here is a toy car coming to essentially collide with the sensor. So now let's see, what is the visual experience of the sensor? What does the sensor see when a car approaches? And you can clearly see now that as the car approaches on the collision course, the intensity of the light falling on the sensors kind of increases monotonically. So this is essentially the scenario. When the two cars are too far apart, the intensity of the light is very low. And as the approach is closer and closer, the intensity of the light kind of increases. So this is what we call the visual stimulus experienced by the sensor. Now let's see what happens if we kind of subject the MOS2 photodetector to the same kind of a looming stimulus. So here the looming stimulus is applied to the MOS2, and here is what we kind of expect, that the photocurrent increases, and here is the experimental data, and you can see that this experimental data matches the excitatory response of the locus, and also depending upon the speed at which the processor is approaching, we can actually get faster to slower response. A fast moving object invokes early response, a slow moving object invokes a later response. So now what we do is we use this programmable backgate to create an inhibition. So what we do is we apply different backgate voltages, and as we keep applying backgate voltages, we can shift the threshold voltage. Essentially, if we apply different pulses, then you can create a response where the current actually decreases over time. So this is kind of very similar to the inhibitory response. And now what we do is we combine the two. While the car is approaching, we actually also apply this programming pulse. And by doing so, we create a non-monotonic trend in the device characteristics. And you can see that the minima occurs before the collision. It's very similar to the locus, except for a maxima, we have a minima. So it's essentially the same principle. And we can detect essentially any kind of object speed using this technique. And you can clearly see that the time to collision, the time to detection is always before the time to collision. But what is more remarkable is that this can be achieved in nanojoules of energy. So the energy expenditure by the device is actually minuscule in order to perform this task. Do I have 5 minutes? So then I will probably continue on this thing, which is the final thing that we are going to talk about is the stochastic resonance, where we kind of use the constructive role of noise for sensory computation, because typically it is believed that noise is a nuisance. You want to get rid of noise when you are trying to detect a signal, and typically it is done in order to increase the signal to noise ratio. So either you increase the signal strength or you reduce the noise floor, essentially to detect that signal. And that is the conventional approach. But that is something nature does not always follow, because certain elements do not have the leverage in order to reduce the noise floor of the environment. So what they do instead is they actually harness the noise in environment. And this is an example from this particular fish called paddlefish, which actually is found in Yangtze River in China or Mississippi River in North America, where the river is actually very muddy. So you cannot really locate your prey by just seeing. So what this paddlefish has developed is this particular organ called rostrum, and it feeds on this thingy called daphnia, which essentially releases this very, very tiny electrical voltages, periodic signal of like 10 microvolts. So the paddlefish is able to find this daphnia using its electroreceptor rostrum. But the problem is, when there was a very interesting experiment which was done, which was shown that what happens if I add a little bit of electrical noise to this very, very tiny signal that this Daphnia is releasing. It was found that, I'm going to summarize this thing, that if you do not add any noise, the paddlefish is able to find Daphnia, let's say up to 50 meters of distance. If you add too much of noise, then the paddlefish is totally confused. It cannot even find Daphnia, which is right next to each other. But with the right amount of noise, the paddlefish is able to find Daphnia, let's say at 75 or 100 meters of distance. And by doing so, it actually increases its survivability and its evolutionary success. So this is essentially what is called stochastic resonance, and it is found not only in finding prey. I mean, it is also good for escaping from predators. In fact, it is found at all scales. It has been used to explain the reoccurrence of ice ages in the earth to the opening and closing of the ion channel. So in short, it's very simple that if you have a periodic signal and if you add a little bit of white noise, then occasionally the signal crosses its threshold and the signal can be detected. This is what we try to do using our MOST photodetector. So here is the experimental setup. We know that MOS is a monolayer material, so it can detect light, but it has a detection limit. Let's say if the light becomes too dim, let's say, for example, in this column, the signal is no longer detected. So you cannot see any signal peak over here, while if the light is very strong, you can detect a signal. So now the question is, the signal that we cannot detect, which is very weak, can be detected by adding a little bit of noise. So here is the experiment. So the first experiment that we did is where we have a periodic signal. You can see there's a bright, a very, very dim LED, but we cannot detect that signal over here because it is very weak and below the threshold of detection of the MOST photodetector. Next, what we did is that we simply added a noisy LED voltage. So this is only noise, and therefore nothing is detected because there is no signal, there is only noise. And you can clearly see that there is nothing happening. And then what we did is we added the noise on top of the signal. So when I add noise plus signal, I can clearly detect the peak in the device. Okay, and this is what is called the stochastic resonance, and that's why I was explaining that occasionally when the signal is below threshold, you cannot detect it using the photodetector, but by adding a little bit of noise, you are able to detect it. But if you add too much amount of noise, then your signal is again lost. So here is the typical curve for the stochastic resonance. This is pretty much very often found in sensory neurobiology, but have not been explored in solid state devices. So this is kind of very new demonstration. And again, the advantage is that the energy consumption for this detection of the otherwise undetectable signal is again of the order of nanojoules to kind of maybe few microjoules. So, and the concept is generic. It doesn't have to be only to sensors. It could be applied to any kind of sensing. So with this, I will probably come to the end of my talk. I would like to acknowledge all my students and the funding agencies. And if you have any questions, I will be happy to take.
Thank you, Dr. Das. Thank you very much for a very nice presentation and also its connection with nature. So any questions, please?
Can I ask a question, Professor Mehta?
Yeah.
Okay.
Yes, please.
So very, very interesting and very nice talk. I'm aware of your work completely. I've got two very short questions. Question number one is absolutely the end. I thought if you want to have a stochastic resonance, you need to have a nonlinear medium in which the noise is enhancing your signal in some sense. So what is the nonlinearity that you see here in this?
Absolutely. I didn't go into the detail of because of this, the time duration, but the nonlinearity comes from the fact that the photo response of the MOST photodetector, there is an echo going on.
Oh, sorry.
Yeah, so the photo response from the MOST photodetector is primarily because of kind of trapping effect, the photo gating effect. And that is mostly a non-linear effect. And that is something we are essentially trying to harness. The non-linearity comes from the photo response. This is not only true for only the photo response, you could also use for electrical signal detection, because any transistor is a nonlinear switch, right? Because your subthreshold regime, you have an exponential dependence of the current on the gate voltage. So essentially the nonlinearity comes from the MOST device itself, both for the photo response as well as for the electrical response.
Okay, good, thanks. That's one. Another very tiny question is your general opinion about 2D material devices as a member of the neuromorphic architecture. Because I understand your work has been primarily to use some of its property in making sensors, which is biomimetic. That's okay, that's great. However, as an intrinsic device, there is no special ability of 2D systems in, I mean, question is that we have been working in similar directions, but can you use, for example, the 2D system or 2D devices as a neuron itself, which can actually harness the learning abilities and so on and so forth? So what is your comment on that? I'm done.
Absolutely. I think that's an excellent question, Arindam. And I think what you mentioned, I mean, some of these properties could be also achieved from other material systems as well. But what we are trying to kind of do is, an integration of sensing, computing, both together. And that is something where the 2D materials provide a unique opportunity, because mostly right now, the sensing part is done by sensors. Then you have a computing core, and then you have other communication core as well. What is so unique about the 2D material is that they can be used as sensor, they can act as a memory element, they can act as a synapse, and they can be doing some computation. So when we think about a compact IoT system, we are not trying to compete with the traditional silicon kind of CMOS technology at this point of time. But this new IoT era that is coming up, there we feel that this 2D material can actually have a lot of promise, because they're low energy sensors, because IoT will require this energy efficiency. And that is something we are getting out of this new sensor design, out of this 2D material. I mean, this is a very short answer. I mean, I could actually have a long discussion with you. Hopefully, next year if we meet together, we can have this discussion. I will keep it short, but the idea is to essentially have an unified platform where the 2D can actually play a very important role.
Thank you. A small question, because you mentioned that from my side, you mentioned that yours is going to be application-oriented or applied direction. So from that point of view, what do you think about the stability of these devices? Because many of the instabilities comes because of the diffusion of electrical contact which you will have with the 2D material. The 2D material is very thin, and just imagine is some amount of aluminum or silver or something is getting diffused into it during the device.
Right.
Yes.
I think that's an excellent question. And I think that, I mean, at the end of the day, your devices really have to be very stable. So I think I didn't get a chance in this talk to talk about this, but I think, I mean, in Penn State, we have this two-dimensional crystal consortium, which is an NSF-funded center, which is looking into this development of this large area growth of these 2D materials. And I work with a lot of my colleagues from material science, and I can tell you that this MOS2 that we are using right now is extremely stable. I mean, even if you do not store it in, kind of in glove boxes, you can store it in simple air, and we can use the same device almost for a year without seeing any reasonable degradation in the property. So what has happened in the last 5 years, we have really put in a lot of effort in making sure that the 2D material is very stable. That is some of them. I mean, I'm not saying that this is true for tungsten selenide, but MOS2, we have been able to make sure that it is very stable, it is reproducible, and we have now measured, we have a new paper coming out where we have actually measured thousands of devices in order to make sure that the performance is consistent.
Thank you very much. Thank you very much, Professor Das, for a very nice presentation. So we move on to the third invited talk of this session, which will be delivered by Professor Max C. Lamy. And the title of the talk is Electronic Device Integration of Two-Dimensional Materials, which is very, very important. And Professor Lamy is a professor at RWTH Aachen University and scientific director of AMO Incorporation, which is a nanotechnology company in Aachen, Germany. He's co-founder of Black Semiconductors Aachen, which I suppose is also another company. He has received the Nano Future Young Researcher Award from the German Ministry of Federal Education and Research in 2006, which is a very important award, I know, and a Leinen Research Fellowship from Alexander von Humboldt Foundation in 2006. He has managed numerous national and international research projects with different partners, and his current research interest includes electronic, optoelectronic, and nano-electromechanical devices and sensors made from novel materials like graphene, 2D materials, perovskites, and other phase change materials, and their integration into silicon nanotechnology platform, which is in fact the most important thing to be achieved if these materials have to be used for in real applications. So we are looking forward to your presentation, Professor Lamy. Please.
Very much. Can you hear me well?
Yes, please go ahead.
Very good. Thank you. So yeah, thank you for the kind introduction. I will talk about indeed today about 2D materials and devices from 2D materials and how to integrate them. And this is the overview. I will give some examples. I will try to show where these devices can compete or outperform existing technologies. This is a prerequisite. If they cannot outperform silicon technology, I don't think they're going anywhere. And I will also try to give a brief introduction to why I think we haven't seen any products in microelectronics based on these materials yet, and what Europe intends to do. So first of all, before I start, thank you for inviting me to this conference. I wish we could have this in person. It would have been a nice opportunity to meet again with some of you. Aachen University, RWTH Aachen University is one of the large European technical universities with currently 45,000 students. We're right at the corner of Germany, Belgium, and the Netherlands, and that's where my chair of electronic devices is hosted. AMO is a high-tech SME. We're non-profit. We're a research foundry, and we run a 400 square meter clean room. Currently have 60 staff members, and we mainly run technology based on silicon, and we try to integrate new materials and show that they have advantages over what you can get from any foundry or fab. And being engineers, we like to think of applications in electronics, photonics, and sensing. And by the way, we do have several students from IIT Delhi, for example, who come with scholarships, and it's always great to collaborate with these students and great to see where they're going afterwards. And one actually just came back for a PhD. So in Aachen, we have also a graphene and 2D materials center. You can see the members here on the left-hand side. The interesting thing here is that we have professors and PIs from basic science, basic physics, like Markus Morgenstern, Christoph Stampfer, all the way to circuit design. Renato Negra is an analog circuit designer. So we collaborate across the wide spectrum of research on these 2D materials. It's also nice to educate students in an interdisciplinary way. We have joint seminars, and we use our infrastructures together. So this is an important thing to be efficient in our research. And yeah, we hope that the center becomes internationally more visible as every day. And we try to attract excellent researchers to the Aachen region. So with that, I would start with my topic. About a year ago, we published a paper where we talked about some of the potential applications in electronics, and we did that together with Infineon, hence the chip here in Germany. And we found in this paper that there's a lot of potential for 2D materials, and we also identified some of the problems why we haven't seen that. And today I will talk about only several of these items. This goes all the way from sensors for IoT to packaging, power devices, NEMS, logic, and neuromorphic. You see that also here. And of course, flexible electronics, which silicon cannot do. And so I think the potential is there. We just need to harvest it in the future. So let me start with photodetectors. And one of the nice things about graphene in particular, but also the newer 2D material platinum diselenide, is that they have an ultra broadband spectral response. This means that you can detect light basically from the ultraviolet all the way to the mid and yeah, even far infrared range. And we know that we have large scale production. Penn State was mentioned as an example where this is being pursued at a very high level. Graphene has very high conductivity. It can be tuned with a gate, and it has flexible as a material, and we can integrate it. So all these are very positive points. The negative point is that although you have broadband absorption, as indicated here, you do have very low absolute absorption because it's only a monolayer. However, still, if we put this on the map, we can say that we can cover this entire range with graphene and platinum diselenide, and we can cover, of course, smaller parts with semiconducting TMDCs. So a very simple device we made some years ago was this silicon graphene Schottky diode. So it's a vertical device architecture where there's a graphene silicon Schottky contact. There's an insulator here, and there's one contact here to the graphene, and there's another contact here to the silicon. And if you measure this device, this is the IV curve, you see immediately that it acts like a diode. If you did this on p-type silicon, you would see that it acts not like a diode, but like an electrical contact, like an ohmic contact, because the graphene in this case was p-doped by the environment. Then we have this clear rectifying behavior. You can do some analysis and you can measure ideality factors and barrier heights of these diodes. And so we moved on to measure the spectral response. And here you see a spectrum from about 300x nanometers to about 2 micron wavelength, and you see this strong peak in the spectral response here in the visible range, and then it drops off and becomes very small here in the infrared range. And if we look closer, we can start to understand what this means when we compare it to a pure silicon diode, and this was a very expensive calibrated silicon photodiode from Hamamatsu. You see that the shape here in the visible is very similar to that of the silicon diode. So you can say we can conclude that most of the absorption in this device happens down here in the silicon. And the other thing we notice here is that the spectral response of the commercial diode is 500 milliamps per watt, and that of the self-built one is about half of that. And then we went on to look in the infrared region, and we noticed also there's a spectral response also in the infrared region that's voltage dependent. So we do see some of the absorption here by the graphene. However, it's a factor of 1,000 lower than that of the silicon underneath, which is 3-dimensional. So that's not too surprising. But then we did something else. We took a scanning photocurrent measurement. So we took a laser beam and we scanned the laser beam across the surface. And for each point, we took a photocurrent map. We took the photocurrent and mapped it out in an image like this. And you see here that for a certain voltage, bias voltage, the photocurrent mainly comes from this Schottky area. And that was what we were expecting. But once we reached a certain threshold, the photocurrent that we detected here in the lower region was much, much higher. And that's actually the region where there's no Schottky contact, because it's the graphene is separated from the silicon by silicon dioxide. And we were not really expecting that. And it took us a while to figure out why we got higher photocurrents where there's no direct contact between graphene and silicon. And it turns out that this threshold voltage corresponded roughly with the metal oxide semiconductor structure here, the MOS structure, and corresponded to the threshold voltage of this MOSFET type structure. And so we created, but beyond this threshold voltage, what we do is we create an inversion layer, and it turns out that these charge carriers then passivate defects, enhance tremendously the lifetime of the carriers, and then make for more efficient photo detection. And with that knowledge, we designed some interdigitated structure like this, where we had Schottky contacts right next to oxidized regions, so that we could utilize this structure in a more efficient way and extract the currents. This is the photocurrent map. And in fact, this picture was taken by one of the IIT master students, and who's now in Stanford. And so you see again that the brightest current comes from the oxide regions. And if you do the spectral response again, you see the blue curve again is the Hamamatsu diode, and the black curve here actually outperforms the commercial diode. And this is just a simple Schottky structure made from graphene and silicon. And so we can make better devices in a very simple way using graphene and include it in the silicon technology. So we also did a similar experiment with a material called platinum diselenide, and this is a material we've been studying together with Georg Duisberg for quite a while now. Platinum diselenide is also a layered material. You can make it by thermally converting platinum into platinum diselenide. You see the nice layered structure here in this TEM image, and it has actually interesting applications in several fields. And again, we did this experiment with the diode, and in this case, it was still the simple diode. And again, we see there's a spectral response in the infrared region, and it's actually higher than that of the graphene. And that's because the layer was somewhat thicker than a monolayer. So we do get this infrared response, and we're currently exploring this further. So another example for a device are these metal insulator graphene diodes. And what you have here is a very simple diode type where you have a graphene electrode and a titanium electrode separated by a titanium oxide insulator, which for electrons is not really an insulator. It's a very low barrier. And this is very similar to metal insulator metal diodes, except in this case, the graphene Fermi level can be tuned by the biasing. So we have a bias-induced barrier lowering, so the barrier itself changes as you bias the device. And in this case, we use these diodes to make up to 60 gigahertz rectifiers, and we also made some circuits from that, but I don't have time to talk about it. So instead, what we also did together with Frank Coppens from ICFO, we functionalized these diodes with quantum dots to make them very sensitive in a certain area of light. And in this case, we chose quantum dots that were highly absorbing at 1625 nanometers. And what you see here is that there's a really nice spot for these type of diodes. So you have 3, 5, and other semiconducting photodiodes in the infrared, and they have very low dark current, which is a good thing. But they also have very low responsivity, which is not a good thing. You also have graphene field effect transistors, and graphene is not a semiconductor, but a semi-metal. So you have high responsivity in these graphene FETs, but you pay for it by a dark current because these things never turn off. So you have this large dark current that you cannot get rid of. And these diodes then introduce this titanium oxide barrier. And so we get the best of both worlds, one could say, or a foul compromise. I don't know which one is true, but I think that this range here in the middle with relatively high responsivity and relatively low dark current is an interesting range. And Frank also has founded a company to commercialize some of these ideas. And so that's, for me, an exciting topic for IR photo detection. We have several other things also going on, and some of them concern MOS2 in various forms, amorphous silicon. The nice thing is that we can do this, make these devices on flexible substrates. And so I don't have time to go into all these details. But that's always a nice added bonus with 2D materials that you can go to flexible substrates. So I would also like to talk about memristors, and there have been different mechanisms proposed for memristors made from 2D materials. And one is a defect-mediated resistive switching, maybe the substitution of vacancies by metals. This has just been published by Dejiak and Wanders group as a potential mechanism for monolayer memristors. There has been suggested some phase change in 2D materials, molybdenum telluride by the Appenzeller group, for example. Lateral ion movement in lateral devices. This was Mark Hersom and co-workers who proposed this several years ago. And then also vertical ionic movement between the van der Waals gaps. And I will talk about this last point because this is something we did. So again, we were making a rather simple structure with a silicon metallic or silicon, highly doped silicon contact on one side, molybdenum disulfide as a barrier material with a low barrier, and a metal on top. So it's a very simple MOS structure. And when we did the characterization, we found in the capacitance voltage measurements that we were able to tune the flat band voltage of this device by applying biases. And the, let's say the bias voltage determined how far we could shift it back and forth. And we looked further into this device because we saw that this is a non-volatile mechanism. And we took some SEM pictures, and we found that actually our MOS2 was aligned vertical. It's not perpendicular. It's not flat horizontally on the surface, but it's aligned vertically, and you can see the van der Waals layers here and the dark gaps in between them. And so we tried to understand what was going on, and then we did some tough SIMS measurements, and we found that we have OH minus ions that can move inside these gaps. And when they move, because they're charged, they change the potential barrier that this thin natural silicon oxide layer forms. And so by doing that, we can change the conductance of the whole stack. And we tested the endurance of this, and we tested also the retention time, and you see the different high and low resistive states here. We also see some asymmetry. We see that it works better for negative voltages, but at least we believe we understand this. We introduced this as a new type of non-volatile device. We also understand, we think, the mechanism behind it. And in fact, it has been shown that a similar effect can happen in 3D semiconductors, 3D insulators as well, by Judy Driscoll from Cambridge University. So we're also continuing the work in this field. Finally, the last type of application I would talk about is MEMS and NEMS, nano-electromechanical systems. And we just looked at, we wrote this review paper just this year where we looked at all kinds of different MEMS sensors based on suspended membranes, because this is one of the potential applications. And here we can use the high Young's modulus of graphene, but also other 2D materials. We can make piezoresistive devices if we choose, even if with graphene with a low gauge factor, but some of these materials have high gauge factors, so they're very interesting for that. Again, we use the flexibility, the stretchability, the low mass. This is important for MEMS, and also in some cases the high surface to volume ratio, which would then also lead to bio and gas sensors, as we heard before, but I'm not talking about that today. So one of the first things we try to do is look at membrane-based pressure sensors. So what we did, we etched a hole into silicon oxide. We then covered this hole with a graphene film and sort of sealed the pressure inside. And then when we changed the pressure on the outside, we strained the membrane. And then because we have electrical contacts to the left and right, we can directly measure the change in resistance of this film. And of course, only the area in the middle is concerned, but we can still measure this. You can see a device here. R2 is the resistance we change with pressure. And we were able to extract the gauge factor of graphene. At the time we started this, people reported gauge factors up to 18,000. And so we were very excited to get this experiment going. We many times confirmed that it's actually maybe 1, 2, 3, 4, 5, something in that area, but it's certainly not 18,000. Nevertheless, because of this low mass and the low thickness in particular in this case, we get very high sensitivity. The thickness goes into the sensitivity by 1/t². So it makes a big difference. And you can see when we normalize the sensitivity per unit area, and this is our graphene device, we outperform silicon and other nanotechnologies by a large factor. This is just 5% of that. So we have superior size and sensitivity scalability of graphene MEMS devices. We also used platinum diselenide for this because it's, well, we also didn't know actually the gauge factor of this material when we started out the work. The nice thing with this material is that you can make it at 400 degrees C, which is compatible with silicon backend of the line. So it's a potential material to be directly integrated to silicon technology. And we found that these platinum diselenide devices outperform even graphene sensors by quite a bit. So you see there's 1-2 orders of magnitude between graphene and platinum diselenide. And then we found an exceptional device that was even higher in performance. Still trying to understand this after several years, but we're continuing this work. And we established that this material has a gauge factor of around -85. And we also think that this is a very, very interesting material to be looked at. Finally, we also looked at accelerometers. And for an accelerometer, you need to attach some kind of mass to your film. And in this case, we used the graphene as the transducer and the membrane, and we wanted to attach a silicon proof mass to this graphene. When this started, I frankly didn't think it could be done. Shugefan, the student, was very ambitious and he wanted to make it happen. And he did make it. You can see the device here. You can see the graphene film from left to right here. You can see that here there's a gap between the substrate and the proof mass. Proof mass is here in the center. And these devices work. They work repeatedly. We've tested them at an automotive company with a professional shaker and tester. And these devices now can provide 1,000x mass reduction compared to the state-of-the-art in silicon technology and 100x area reduction. So this is actually very nice. And the long time until this happened was worth it because Suga now has these very nice papers published last year. So MEMS are a possibility. And finally, we also looked at microphones. This was done together with Infineon, so they provided these commercial MEMS structures, or they used the commercial processes to make these specific structures for graphene membranes. And we measured the frequency range, and what you can see here is that we have no resonances in this frequency range. And typically with silicon microphones, you do have resonances that disturb the signal in an area where they shouldn't. And with graphene, we don't see that. So we have a much wider frequency range, and we're currently also looking further into this. With that, I would like to point out some of the problems. And of course, we can grow materials now, and we can grow them at wafer scale. But typically, the growth temperatures are high, and they include some kind of catalytic metal on the surface. And so this metal often gets incorporated into the graphene and the other films, and then becomes get stuck there and can become a contaminant. The transfer process to transfer it onto the desired substrate is a problem. It's nice because we can transfer to virtually anything, but on the downside, it's a problem because we cannot really control that, and it depends on the person who does it more so than the environment where you're at. Electrical contacts, I think, are solved for graphene. We can understand those contacts very well now. We can make them very ohmic. For 2D materials, semiconducting 2D materials, I think this is still an open topic. Etching with atomic layer etching to make etch stops, like here in this integration scheme, for example, or in this case not. And encapsulation, the dielectric environment. We saw in the talk before by Professor Das that there's trapping and photogating, and well, if you use it in the way he did, that's a very good thing. If you want a stable device for, let's say, a CMOS circuit, that's a very bad thing. So one has to also look at what this is for, but the encapsulation itself is a problem. And as you may know, in Europe, we have this large 10-year initiative, the Graphene Flagship. And the Graphene Flagship has understood this problem, that there's research going on from a very low technology readiness level, and there are some sub-projects in the flagship that address higher TRL research, but none of the commercial foundries and manufacturers have taken up to the technology. And that's why the flagship just launched a pilot line. They call it 2D experimental pilot line. And the goal here is not to make a specific device, but to develop the technology. And there are now 3 places, IMEC in Belgium, AMO in Aachen, that's us, VTT in Finland, who run let's say, pilot line clean rooms, where in the future we want to establish a wafer scale technology that people can use using a PDK. Then we also have several companies, Extron, who grow materials, Oxford Instruments, who make encapsulation layers with ALD, Zeus Microtech, where wafer bonding is a big topic, Graphenia, who make graphene, and a chemical company to make the suitable resists, because those are also still problematic with 2D materials. So together we want to solve some of these problems, and then we want to transfer this possibly to the European industry, because it's a European project, and we have a industrial advisory board where many of the large European semiconductor fabrication companies are present, and we want to transfer this to Euro practice so that people can use these PDKs to make some designs, and then we can make multi-project wafers in the future. With that, I would like to thank you for your attention. I have shown some of the research going on in Aachen on MEMS, electronics, and optoelectronics. Didn't have time to talk about everything, of course. And yes, I think we're going from Scotch tape to a very high technology readiness level now. We have this experimental pilot line. We founded a company. There are many other companies with 2D materials coming up. And I hope that we will continue this until we see products, and that would make me very happy as an engineer who likes to see research turn into products. Oops, wrong side. Thank you very much for your attention. This is our group, by the way, before Corona. This is after Corona. Social distancing everywhere.
Thank you very much, Professor Len. Very nice presentation. And especially I like the last few slides on 2D pilot line. And I think Professor Ghosh is there. And I think in India, we should do something in that direction. And your talk is open for question. Question, please. Yes, Professor Ghosh.
Yeah, very, very interesting talk. I enjoyed the different channels. So I have two questions. One at a generic level, and what the directions of the technology development that you just showed are exactly, the global trend right now. We're starting from the NEMS to photo detection and so on and so forth. Do you find any of these channels can actually compete in terms of commercializability with the existing technology? Whether it is silicon based or whatever it is. So that would be really interesting to know. I mean, whether there is a cost benefit advantage.
Yes. So I think the cost benefit today is not there because the technology is not something you can buy as a turnkey technology, right? I mean, if semiconductor industry at some point can buy a graphene deposition tool or MOS2 deposition tool from one of the vendors and include it in their line, I don't think there's any cost disadvantage. It will just be another process step. So I think the scalability is generally there and it will happen if there's an application. Now, for some of these applications, I think that, yes, there are clearly advantages. So for the infrared photo detection, this is already going to an extremely high level. We work, I didn't include the slide, we work with a company called Emberion, and I can talk about it because it's a publicly funded project. They are a spin out from Nokia, and they try to commercialize infrared cameras based on some of these technologies that I've shown. They have graphene in their stack. I cannot talk about the details, but you can buy today, or you can even get from them, single pixel demonstrators. You can get line arrays with underlying CMOS. So we're already doing CMOS 2D material co-integration in the back end of the line, like I showed in the schematic here. This is something that's going on today. So clearly an advantage. The same thing I mentioned, Frank Koppen's company. They have a big investment from automotive market. So this is definitely something where can make a big difference because you can make sensors for a few euros instead of 500 euros, which is the current technology. So yes, there are other fields where also there are clear advantages. We have a project on carbon dioxide sensing. The same, there's a factor of 10x probably in the cost savings if we can integrate this infrared part. So the answer is yes, but the problem is here. The pilot line is the problem. I mean, it's not the problem. It's a potential solution to the problem. We need these companies here on the right to start producing. Then the cost is no issue.
Perfect. Just a very short, detailed, specific question regarding, because I know Frank Koppen's work for a long time, particularly the quantum dot graphene heterostructures. Even in terms of functionality of those devices, they usually work on this photoconductive principle. So they would be very slow in a certain sense, and and also the scalability of the multi-pixel domain. Are there, because I think the optoelectronics will probably come to the market first, if I'm not wrong, but
I would agree.
Yeah. So, are there technological solutions to such of these specific problems with the graphene heterostructure-based optoelectronic systems?
So, I think the same thing applies to the nanoparticles. I mean, it's not something that is in most fabs, but on the other hand, if you look at the flat panel market where nanoparticles can be in a product, I think there's no technology barrier to that, in my opinion. And I mean, Emberion, they are making now VGA resolution cameras already today that you can get as a pre-product and so on. So yeah, I think it's not a fundamental problem, and nanoparticles are in products already, and graphene is probably going to happen. The other 2D materials, I mean, we heard from IMEC and others. There's this hope that we can make ultimate CMOS with these nanosheets. Then we get nanosheet transistors that are ultimately small. They still have good mobility, even though they're very thin. I mean, we 10 years ago we made silicon transistors with less than 1 nanometer film thickness, and They are horrible. I mean, they switch on and off nicely, but they have a mobility of 3. And so the 2D materials are even thinner than that, and they don't suffer so much from the remote scattering and remote phonon scattering and so on. So from that point of view, maybe we'll even see them in ultimate CMOS, even though I'm afraid Europe won't be doing that. It will be maybe Taiwan or South Korea.
Any other question?
Thanks.
So I think let's thank Professor Lemme for a very, very nice
Professor
lecture.
Mehta, somebody
And-
has okay. Professor Mehta, somebody has asked this question, okay, in the
Please.
chat. Is that for this talk or the other talk? Let me see. How good this 2D membrane is holding the vacuum? Is that the So somebody, Chotrai Soren, how good are 2D membranes in holding pressure or vacuum? That is the question from a PhD student. So if you can answer.
That's a good question. You see the image of the membrane on the left-hand side here. So when we started the work, there was only experimental work on exfoliated, sort of nearly perfect graphene, and the message was that it can be airtight even to helium atoms. And because we are engineers, we usually try to work only with CVD materials that are scalable and so on. So we knew the quality was not going to be as good. So there is some leakage, but my colleagues in Delft University, who are also working on similar structures, recently found that, okay, first of all, we need to go from monolayer to bilayer because the yield and so on is much better. We already published that some time ago. And then when you do that, the gas leakage rate is actually quite low. And then it turns out that most of the leakage actually doesn't go straight through the graphene here, but it goes throughout the side. So if you see the small membrane here, it goes out to the side between the graphene and the substrate, in this case, silicon oxide. So there's leakage there. And then they sealed off the graphene edge with an additional process, and that reduced the leakage rate by a lot. So I think for most pressure sensing applications, some leakage is tolerable, and it's very small if you go to bi or tri-layer materials where you have defects, but they are usually not located at the same site. So then it's okay. Completely sealing, no. I think that's impossible with these membranes.
So, Professor Lemme, thank you very much.
Thanks a lot. I hope to see you in person. Not too long.
Yeah. So we go to the next presentation by Dr. Jyoti Jaiswal from IIT Roorkee. And the title of the presentation is Vertically Aligned Edge-Oriented Molysulfide Hybrid Thin Films Decorated with Palladium Nanoparticles for Room Temperature Hydrogen Sensor. Yes. Dr. Jyoti. Uncle, Jyoti is there? Professor Goswami. Dr. Jyoti is there?
Right? Yeah, no, I am not able to see her here. She has been already informed.
So what is your suggestion now? So we close the session?
We can close the session. Oh, just give me 5 minutes, 2 minutes at least. I would like to call. I have her number.
No,
I
it
think,
is
let's use this intermediate time for, if there's any question, because we have all the invited speakers here. Professor Arindam Ghosh and Professor Das and Professor Lemme. Professor Lemme, can we continue discussion with you? I think I have a question regarding, you mentioned electrical contact is a problem with 2D materials.
Absolutely.
Or electrical contact is a future research direction. So it is just that difficulty in making ohmic contact, or it is the stability of these contacts also issue? Because
so I think the first problem definitely is the making it a better contact. That's one of the problems. But the stability is a general issue, I think. I mean, not just the contact, but the whole dielectric environment and variability and stability. Those are definitely problematic at the moment.
Okay. And you mentioned regarding in your lecture that the thickness of the monolayer, for example, is very small, and that affects the photodetector properties. So,
Yes.
so what is the solution like that? That means one should work for 4 or 5 monolayers, or what is the how this problem can be sorted out? Because the absorption is very less, the photo response is affected.
Absolutely, that's correct. Yes, I mean, I think for if you know the specifications of the application, you can always tune that and use several layers. I think that's one of the solutions, and you can get to 20% absorption quickly. Beyond that, it's graphite, so then it becomes maybe more difficult. But the other option, of course, is to make more integrated structures. I didn't talk at all about silicon photonics and silicon nitride photonics, where we use graphene and 2D materials as detectors and modulators and heaters and so on. So that I mean, the nice thing with graphene is if you can tune the Fermi level, you can make it transparent or absorbing. And of course, that way you can make very, very simple absorption modulators. And then the Kramers-Kronig relation gives you also the option to go for phase modulation. So all these things can be integrated into the silicon photonics platform. And that's we do have another pilot line in AMO, so that we have our own photonics fabrication, and we have a whole group working on that. Let me not go into detail, but that's also what Black Semiconductor is about, the company that we founded last year. So I think there's a lot of, because there also you do not come to the graphene or the material in a vertical way with the light, so you don't suffer from the low absorption. The light is guided, and you put the graphene on top, and of course then you have much more interaction between the light and the graphene, and you can get up to 100% absorption if you make it large enough.
Okay, thank you. So before I open, before I give the question, I just want to have a question that can you tell us how India can participate in that 2D pilot line project which you have? Is it possible? Is there a possibility, or?
Well, one thing is we are currently, first of all, we have to, of course, establish, let's say, standard process flows. I mean, today we are already working on wafer scale, but it's always very specific to a certain customer or someone who wants to go for it. But once we have established this PDK, this process design kit, people can apply for even getting on a multi-project wafer, so that you can get devices or chips out of that.
Okay.
Let's say on the development itself, I think one would have to see about collaborative programs by the European Commission and the Indian government, or the German. I mean, this can also work on a national level, of course. And I think there are many programs. I mean, of course, for basic research, there's the DFG, and we have currently still waiting for the reply on our proposal from last year. But that's fundamental research. But for the applied research, there are recurring opportunities. And I mean, Europe is trying to become more autonomous in the chip making now. We've realized, fortunately, finally, on the political level, that these chip wars between the US and China, they're not going to help Europe. So there's going to be investments. And I know that India has made similar announcements that, yes, we can do software, but we need to do hardware as well. And that was on one of my first slides. I always say we cannot talk about digitalization without ignoring the hardware. And now we talk about artificial intelligence. We make all these, startups that program apps and whatnot. But if we don't control the hardware, it's not secure, and we rely on vendors to supply these chips that then can be spied on and so on. So it's a political issue, and I would agree that India and Europe are probably in the same boat in this, because India also has this strategy, as I know.
Thank you very much. So
I have a quick comment on that.
yeah, you can ask the question. But what about the next presentation? Do we have or we don't have?
Yeah, we
I think
don't
we
have, so we
Okay.
can
So Professor
close the
Ghosh,
session
you can
after.
ask the last question.
Okay. No, that's I don't agree. One of the problems that we have now is that most of the collaborations are by country, mutual collaborations. There's nothing in collective form. That means whether there's an Indian government and European Union in whatever form there's nothing of that sort as far as I understand. Probably this is something which will be required, but I have personally been part of a large number of different bilateral projects with in Europe, Spain, Sweden, UK, or whatever it is. So, as this specific point of where collaborations can occur, probably the next step in collaboration will have to be between a collective manner rather than plainly with bilateral. And then I'm sure the scientific part will develop much easier. And as a matter of fact, absolutely correct that it needs to be based on the high quality material development. A 2D material development in a large scale, in a wafer scale, and multiple variety of it. I had a small question in that regard, actually. Talk was primarily on graphene, but Saptoshi just gave a talk just before that. It looks like that we should also invest in developing other 2D materials at the wafer scale, which means TMDCs in particular. The MOS2 has already moved quite a distance. I do not know to what extent Aachen and other places are investing in making large wafer scale 2D materials of non-graphene origin. And the second point is to what extent the investment is on in making hybrids at the wafer scale. I know graphene and quantum dot makes very good photodetector, but graphene and MOS2 makes even better. So the question is, are there initiatives to create complex structures in Europe at the wafer scale other than graphene?
I think this goes as much to Professor Das as it goes to me. Maybe I can quickly say that the company Extron, that is located in Aachen, is a startup from the 1980s from Aachen. They make these MOCVD tools for the semiconductor industry, and they're very successful in the 3.5 market. They have invested quite a lot of money in developing MOS2 or TMDC deposition at the wafer scale, and so now they've just announced a 200 millimeter tool that they can scale up to 300 millimeter. And IMEC, for example, does a lot of research together with big companies, Intel, Samsung, TSMC. They are really trying to incorporate these semiconducting materials into the process. So I would always say, yes, these other materials are maybe even more exciting about some of the applications than graphene.
Sure. So in fact, I also wanted to add that IIT Delhi has a collaboration with NCTU, Taiwan, and there also there's a lot of emphasis on growth of 2D materials on wafer size in collaboration with TCMC and other companies in Taiwan. So I think
Aachen University also has a collaboration with NCTU, so maybe we should.
So we should have a try. Sure. Thank you. So I think Professor Goswami, I think let me thank all the three invited speakers for very, very nice presentations, starting with Professor Arindam Ghosh touching on more basics and thermoelectric and electronic transport, Professor Das on applied areas, and Professor Lamy on multiple applications of 2D materials and giving us an overview of 2D research at Aachen. Thank you very much. It was very nice, wonderful to have you in this session. Thank you very much. And let's hope we meet soon.
Yeah. So with that, I thank Professor Mehta regarding his session chair, and we'll meet again at 2 o'clock. And Professor Sajal Dhara is the chair of that session, and Professor Andres Gomez will be the first person, is the invited speaker. So let us meet after the lunch. So we all hope that you enjoy the session, and let's continue to do these sessions. Okay, thanks a lot again. Yeah, so let us meet at 2 o'clock.
Thanks, everybody.
Thank you. Bye-bye.
Bye.
Hello? Hello?
Hello, Professor Andres. Yeah.
Hi.
Hi. We'll start the session. This is Ankur Goswami. We'll start the session maybe after 15 minutes. This is 1:45 here, 1:45
Okay.
p.m. So maybe another 15 minutes. So
Sure.
2 p.m. sharp we should supposed to start. So
Okay.
you can wait for time.
I checked already the presentation like few minutes ago and it was working okay. So
Okay.
I think I
Okay.
can.
Yeah.
Okay, I'll be sharp.
So
I'll be sharp like 2 minutes before two there.
yes.
Okay.
Fine. No problem. No
Okay.
problem. Yeah. Okay. Thanks.
Thank you. See you.
See you. So I think we can start now regarding how many.
Yeah, we can start now.
Yeah. So let people join. Already 8 participants are there. Yes. Yeah. So let us wait for 2 minutes. Right now it is
Yeah.
1:57. Yeah.
ఎంతున్నారట బాబా అందరు ఇంత ఎంతున్నారటే
మరి ఆనందాలంటారు
లేదు
మంచి రోజులు క్యాబిన్ చూసుకోపోయినావు ఇక్కడ
అక్కడికి వెళ్ళాలి ఇంకా అక్కడ కూర్చొని చేయాలి క్యాబిన్ ఇక్కడ
పవన్ దగ్గర క్యాబిన్ ఉండే కదా
ఎవరు వచ్చాడా
వచ్చిండు కనబడ్డాడు అప్పుడు
Ankur,
I would request. Yeah,
Ankur,
yeah.
can you hear me?
Yes. We can
good.
hear it. Yeah. So I would request those who are not speaking kindly mute your microphone. So there are noise coming in. So with that, we can start today. I think all of you can hear me. Just one of you can say yes. That will be helpful.
Yeah.
Okay. So yes. So my name is Ankur Goswami. I am actually convener of this symposium. Welcome to the Icee 2020 conference symposium 2D materials and devices. And this is the session 2. Already we have session 1. Now in this session we have total 4 speakers. 2 invited speaker and 2 contributor speakers. Professor Andres Gomez from Madrid, Spain, and Professor Saurabh Lodha, IIT Bombay. These 2 invite speakers with us, and Professor Shaheen Sorifi and Naveen Mr. Naveen Boka, Mr. Shahin Sharifi, and Mr. Naveen Boka. After them, they will have a talk. So this session will be chaired by Professor Sajal Dhara from IIT Kharagpur Physics Department. Professor Dhara is a professor in physics, and he is working on optoelectronics devices. So with that, I would request Professor Dhara to take it over and introduce our speaker for this session. Yeah, over to you, Professor Dhara.
Okay. Thank you, Ankur and Samresh, for inviting me for chairing this session. So I'd like to introduce the first speaker of this session, Dr. Andres Castellanos Gomez. And Dr. Andres Castellanos Gomez is a tenured scientist in the Spanish National Research Council. He explored noble 2D materials and studies their mechanical, electrical, and optical properties with special interest on application of the materials in nanomechanical and optoelectronic devices. He is the author of 140 articles in international peer-reviewed journals and 6 book chapters. He was awarded an European Research Council starting grant in 2017 and has been selected as Emerging Leader 2020 by Journal of Physics Materials. Included in highly cited researchers in 2018 and 2019 lists of Web of Science. Selected as one of the 2018 Emerging Investigators by Chemical Society Reviews and selected as one of the top 10 Spanish talents of 2017 by MIT Technology Reviews. He has been also recognized with the Young Researcher Award Experimental Physics of the Royal Physical Society of Spain 2016. With this very brief introduction, I would like to invite Dr. Andres for the talk titled Stentronic Devices Based on 2D Materials. The duration of this talk would be 25 minutes and then followed by 5 minutes of discussion. Okay, so Dr. Andres.
Thank you, Sahal, for the introduction, and thank you, Ankur, for the invitation to give this presentation in this conference. I wish you have a good afternoon over there. So I'm just starting my morning here. So let me share my presentation. It should work. So you see it okay?
Yes, we can see it.
And I think of all the proper now is based.
So sorry to interrupt, Professor Andres. I think some of the audience have not muted their microphone. I'll request all of you to mute their microphone when not speaking. It's a lot of noise coming in. Yeah, please go ahead. Thank you. Yeah. Sorry.
Thank you.
Yeah.
So the straight is a term used to refer to the field of research in material science and benchmarking, where we here in functional devices. The keywords here, so training and the so you get Stringtronics. Okay. Now use train. Time. So software. for the based on the and this strange detector is to make what you might for topic. In the detector, this is what we want to make with our strange field. Okay, so we want detector version of the adapter for detector that we have in the UI. Okay? Alright. Then the thing is strange. So we have many different materials, functional materials. So why to focus on two-dimensional materials? Certain specific properties of two-dimensional materials are suitable for string environment. Conventional string engineering with three-dimensional materials is typically done by a force reaction or
Excuse me, Dr. Andres. Excuse me, Dr. Andres.
Yes.
So there is some problem coming, maybe some internet issue. Could you please check the connectivity? We are having some trouble hearing it in a continuous way.
There are some interruptions, Professor Andres, I think from maybe from your end microphone or something. We tried
So
to stop
over
it.
here, the connection looks okay.
Okay. It seems fine now. Please continue.
Please continue. Yeah.
Okay. So it seems okay. All right. So the approach to apply strain to three materials is for detection of the different lattice. When this detection basically what we to transform layer and risk cannot see in time. Once you roll one of another one, strain is fixed. It is strains are all. So so you cannot let's say 1.5% actually. This is very when you use two-dimensional materials are like here for a second here. Because these products can be full PPS, can be, like maybe here where we have a layer of two-dimensional material with a mesh over top. You can use it, for instance, by very large center. Okay, and you can the kind of FD in order to choose this training. So this is completely different to this training. Now we can training that we can change. So that materials can sustain very large variations up to 10-50 for break. Okay, so these are documented, and also last year is the structure of the material is very sensitive to compress it, and you put it in the bag by the energy of the region, and that estimation of how much you're opening or closing the bag. Very to strain. Okay, so a little change in strain induces a sizable change in the band gap. Makes dimensional materials to be particularly suitable for electronic. And I believe electronics of two-dimensional materials is one niche application for today's. Okay, so maybe two-dimensional materials are not going to really see in a short time scale, you know. But if we found a situation where no other material can be, then this electronics kind of a new, maybe one of them. Okay. But so far, most of the studies you can find in the literature are fundamental studies, so not studies. Okay, so the study is before. So you basically apply information and you use an optical tool like essence or reflectance, monitor the changes in the band gap. But you not exploit these changes in the band gap in a fundamental device. Okay, so there are just few examples in the literature. One of the first ones is from Sandro from Icee. Electrons. While you invent in this brain here how they will in terms of the applying more and more deflection to the suspended layer. So basically this was a strain tunable resistor. So it's the first functional device exploring strain as a tuning not fabricated with two-dimensional material. Approach is very difficult. You need a functional AFM, a operational AFM to operate your device. So you don't want to use a machine that costs $100,000, you know, to operate your phone detector. And the other thing is that if you need to have a tip on top of your device, it's going to be very cumbersome to integrate with electronic measurements in what you want to use in the device. Okay. So this is not the optimal electronics. There are other recent processes where they again to the strain to dimensional device. Full measurement here on graphene, but they are just focused on magneto transfer moments on graphene, so not exploiting strain coverage of the device, but to measure fundamental properties of graphene and not now work different for mechanical. I think so. Not in this context. And we were thinking that we were successful in finding cheap and dirty, so complicated problems, and we came up with a good geometry to fabric frame that this is that unit. And this flat exploit and stuff. to apply a biaxial strain to the material. And this is what we have done with for expansion. It's shadow application. We stamp a single layer of the mesh. And right electron like this. The way we do similar here in the ball that electrons exactly. Okay, so you can see now the technique allows you to fabric this. So you can just start principles of your very simple. So the geometry different illumination wavelengths. All right, yeah. Okay, so with different wavelengths. So %, tension. Okay, so we can change the strain in a broad range. Okay, and first thing we want to A and B. Basic. And the first is 5 Russian. So we then the red. If we compress it fully, it's the blue. But also, if you're interested in spectral rate of the the maximum wavelength able to
sorry to interrupt you, Professor Andres. So actually there is a disruption in the voice. So can you please check whether if you can turn off the video, whether it is improving? Really sorry for this inconvenience.
To stop the video, then?
Yeah, then you can continue. Just turn off your video and see whether it is improving.
Sorry, I don't know how to do. What should I do? Ah, here.
Yeah.
There. Yeah. Okay. Okay. Here, maximum wavelength your detector can detect. And now this wavelength. We see that it's 70. Another than 8 years away, in a wide range, actually. This is the substance. You observe in the in your device when you're applying retrospect and the responsibility due to this thing. But all of the actual strain is the temperature because we have changed the temperature of the substance in order to apply our biaxial strain. So the way we can handle these two features is to fabricate these two short. We fabricate has a large thermal expansion. All set of devices with on that's I mean equal compared with carbon. Two sets of devices to the same temperature, 25 degrees, and we use that the photo response. It's mainly due to the biaxial strain. On the second side, we have more contributions on small negligible enhancement of the photoresistivity. Basically, to the biaxial strain in our devices. And one of the important features of our platform is the change in the temperature of our temp. We can change the strain of our current when we strain from 0.16 of strain, we have seen the shift towards that, and also we enhance the photoresistivity device response. Here, what we see basically we are the temperatures. We at the device for the user, it's like for 30 minutes to go the adaptation to change the condition. Okay, 20 seconds, I will say that we are not doing it so bad. So this here is not the response time of our molybdenum sulfide photodetector. Stage to thermalize because we're using a full thermal state. We are now detector here, and if you use a micrometer in this figure, it becomes fast. So we have so thermal I think with this I come basically to the conclusions part. So I showed you how we can exploit mechanical information supply that we in order to modify the output characteristic dimensional material space of electronic devices and figure out how detector under pressure. It's a fast detector with low responsivity and a narrow band pass. While if you have a molybdenum disulfide under tension, with a high band spectral rate. Two examples here. Extremes. They not even push here and stop at the position we want. Okay, this is very important. So we can bring the output characteristic of our device to the static emissions that we have. I have talked to all people involved in this project, especially most of the my students is about to grad next week. Basically, it will be defending the thesis, but still very left. Results are and review our post review very left. I just got appointed 10 second list in the research council, so it's a T for our group. We are losing the battle, but he will become a nice colleague to work with in the research council. Yeah, we have was out about tunable in selenite photodetectors that are similar to this, but they have a much stronger strain sensitivity. That, of course, the for this, you can.
Thank you, Professor Andres. Now the session is open for questions. I cannot see any, so if you have any query, please you can directly ask, or you can also write it in the chat box.
Okay, can I ask a question? This is Arindam.
Yeah. Arindam, please go ahead.
Okay, good, thanks. This was a very interesting talk. The quick question here is, do you see any of, or have you looked at any of the photo detection with the gate voltage changes, or it's only strain that we are looking at?
Oh yeah, that's the next question. Currently, we use say
Yes.
Okay. Is there any question?
Yeah, I have one more question, if I can ask. This is Saurabh Loda. Thank you, Professor Gomez, for your nice talk. I had a simple question. Have you also looked at the detectivity of your photodetectors, and does that modulate, does strain modulate the detectivity of your device?
Yeah, so we need to look at the small bits. And he was
I see. No, but does and it depends on whether it's tensile strain or compressive strain, is it? Okay. I see. Thank you.
I have a related question, if I can quickly ask you.
Sure. Please go ahead.
Okay. No, the question is, the change in the compression and the, is also connected, or tensile, is also connected to the doping that probably can take place. So whether the response change that you are seeing is connected to actually through tension or the true strain to doping. Is there any understanding of that? Okay. Perfect. Thanks very much.
Okay, so if there is no more question, I think let's thank the speaker for a very nice talk. And now we'd like to continue with our next speaker, with our next talk by Professor Saurabh Lodha. So I'd like to introduce before we start the next talk. Professor Lodha, are you?
So
yeah.
So can I?
Yeah, sure. So let me quickly introduce the speaker. So let me introduce Professor Saurabh Lodha from IIT Bombay. He did his BTech degree in 1999 in electrical engineering and did his PhD from Purdue University 2004. He worked in Intel Corporation, Portland, USA from 2005 to 2010 in the development of research and development of 45, 32, and 22 nanometer silicon CMOS technologies. He joined IIT Bombay in 2010. His research interests span devices and materials in the area of advanced CMOS technologies, 2D optoelectronics, and gallium oxide power electronics. He was awarded the Swarna Jayanti Fellowship 2017 and the Young Career Award 2020 by the Department of Science and Technology, Government of India. He has authored 71 peer-reviewed journal publication and 8 patents. His work has been cited nearly 2,800 times. He is a senior member of IEEE and has supervised 12 PhD students and 5 postdocs. With this brief introduction, I would like to invite Professor Lodha for the talk.
Thanks, Sajal. I hope I'm audible.
Yeah.
Yeah, okay. Trying to see if I can turn on the video. But once I start sharing, I'm not able to see the...
Okay. Okay, so you can unshare and turn on the video and then you can share it again.
Yeah. Wait 1 second. Let me turn on my video. Yeah. Okay, now let me start sharing. Okay, can you see my screen?
Yes, but it is not, yeah, right.
Okay. Thank you, Sajal. Thanks for that introduction. And in fact, my talk is actually a continuation of one of the topics that Professor Gomez mentioned about the role of traps in photo detection. I'm currently at TU Delft as a visiting faculty, and so I'm giving my talk from the Netherlands. So I'm in the same time zone as Professor Gomez, I guess, in Europe. So my talk is on fuel layer TMDs and their heterostructures for high performance photo detection. And the work has been done primarily by my PhD students here, Abin Verghese, Sayantan Ghosh, and Kartikeya Thakkar. So this is an outline of my talk. I'll talk about optoelectronics using 2D layered materials. And then the main focus of my talk is on responsivity and speed trade-off in suspended, and basically the trade-off of responsivity and speed in 2D material-based photodetectors. So I'll first start off with giving an overview of this trade-off in RES2 phototransistors using suspended and supported transistors. And then I will show you two examples of how you can engineer this trade-off. One is engineering the trade-off in WSC2 phototransistors through a lateral PN junction. And then later I'll show you how you can use a heterointerface of WSC to RES to engineer the responsivity and speed. So that's the brief outline of my talk. So let's look at 2D materials and applications. I think there have been several talks in this conference now that have highlighted the benefits of 2D materials. There are various kinds of 2D materials and various kinds of fields that they have impacted: spintronics, electronics, sensing, heterostructures, and as you heard, Professor Gomez talked about straintronics. So there are many areas of application for 2D materials. It's also very interesting from a conventional transistor perspective. One of the smallest transistors has been demonstrated using molybdisulfide, a 2D material. So there's a lot of interest in 2D materials, and my group specifically focuses on electronic and optoelectronic devices using 2D materials. Just to give you a very quick one-slide background of my group, we work on electronic devices, looking at contact resistance, doping, and noise. This is some of the work that we have done, looking at the role of traps and hysteresis, suspended devices and noise measurements, and then doping in to form PN junctions in MOS2, and so on. We also do a little bit of modeling, not a whole lot of modeling. We've done some TFT simulations in NEGF transport in 2D materials, looking at, for example, RF performance of 2D materials in this paper in 2018 using NEGF. And then finally, our more recent interest is in optoelectronics. So we've looked at plasmonics on a single layer MOS2. We have also looked at some of the photodetectors using 2D materials that I'll talk about today in this talk. So my talk basically is focused on the photodetection aspect of our work. So when you look at optoelectronics using 2D materials, why is it so exciting? It's because you have a large library of materials with variable band gaps. So you can cover a large part of the spectrum all the way from visible to infrared, and with high absorption. So despite being very thin, they have high absorption, and so you can get very good optoelectronic performance. They are transparent and bendable. So as Professor Gomez showed, you can use, you can easily bend them, and you can introduce strain, and then it makes it also interesting to use them for wearable devices in the future. And the other interesting thing about 2D materials is that you can form these atomically sharp PN junctions, which result in efficient photo generation, carrier separation, and low dark current. So that makes them interesting for PN junction-based devices. And some of them are good for high-speed applications such as graphene, black phosphorus, and so on, which makes them easily integrable with optical communication devices. So a lot of interesting applications are possible, and a lot of interesting material properties that 2D materials do. If you look at literature reports in the area of 2D materials, this is something that was collated by one of my students. Excluding graphene, if you look at the number of publications, and just looking at TMD, optoelectronic devices, in the past 7 years, there's been a huge growth in the number of publications. And the HS here stands for heterostructures. So you can see individual materials and then a large chunk of papers coming out on heterostructure devices. This is as of 2019. I'm sure this number has grown now in 2020. And there are a plethora of devices that people have demonstrated various architectures and various kinds of properties all throughout the years from 2008 up till now. So a lot of abundant literature there in terms of 2D material-based photodetection. So what is it specifically that we are looking at in our group technically? If you look at 2D photodetectors, their performance, and if you plot two parameters, which is responsivity and response time, you find that a large number of papers lie in this group here. And what you see is, if you look at a silicon photodiode or an in-gas photodiode, which is commercially available, they are not very high response. They don't have very high responsivity, but they're very fast, and they lie somewhere here. And this is the corner that you want to be in. You want to be fast and you want to have high responsivity, right? So what you see here is that there is a fundamental trade-off between responsivity and speed, and that happens because responsivity depends on gain, which depends on lifetime, and speed, it depends inversely on lifetime. So while you can have high responsivity, you can typically lose speed, and when you can have high speed, you typically lose responsivity. So there you're basically traversing you're moving in these corners across this plot. So there's a basically fundamental trade-off between speed and responsivity, which Professor Gomez also showed in his data. For example, you could see that there were faster devices with lower responsivity and devices with high responsivity but slower speed. So there is this fundamental trade-off. So one of our first works was to study the effect of traps on speed and responsivity trade-off, whether we can establish this trade-off in a photodetector. So we fabricated two kinds of photodetectors. One we call the supported RES. We chose RES because RES was an interesting material for optoelectronics, and so we chose RES, and we made two kinds of devices. One was a supported device, and one was a suspended device. And we wanted to study the impact of traps on the optoelectronic performance of these two devices. So, for example, this device, which is supported, will have more traps, but it also has good gate control, whereas the suspended devices will have less traps but poorer gate control. So we wanted to see the impact of traps and gate bias on the overall optoelectronic performance of these devices. If you just look at the transfer characteristics of these two devices, you can see that the effect of the poor gate control in the suspended device, you can't turn it off very easily. It's difficult to turn it off because it's suspended, whereas the supported device turns off very easily with gate voltage. In photodetectors, there are two main aspects. One is photoconduction, where you see an increase in photocurrent, and the other is photogating, where you see trapping of carriers, and because of that, one kind of photocarrier, and because of that, you see a shift in the IV characteristics. So one is photogating and one is photoconduction. When we illuminate our devices, the supported device and the suspended device, we see the effect of both photoconduction and photogating. So in the supported device, we see an impact of photogating, but we also see effect of photoconductivity, while in the suspended device, we primarily see photoconductivity. Now, there are two kinds of traps. There are intrinsic traps in the semiconductor, which are part of the semiconductor itself, and then there are extrinsic traps where you can exchange carriers with an dielectric such as SiO2. So we have to see that in case of the suspended device, it's mainly the intrinsic traps that play a role, whereas in the supported device, you have intrinsic traps as well as you have interface traps. So you have larger number of traps in the supported device. So this brings me to a key slide, which shows you the low frequency dynamic photo response of these devices. And I have 4 panels here. So first you take in the order of decreasing effective trap density and increasing speed. This is the first device. Suppose you have the supported device, which is turned off. So you have here the orange is the photo generated carriers, and the green are carriers induced by the gate voltage. What you can see is that you have large number of traps here near the conduction band, but you have very few carriers. So you have essentially a large trap density, which gives you a large photocurrent. So in this plot here in E, the laser is on when it is yellow, and the laser is off when it is white. So you're switching the laser. And so what you see here is that you have a large photocurrent and a large decay time. So you have high responsivity, but poor speed. If you go to the next case where you have a suspended device and you have turned it off, as the gate voltage is negative here, you have less number of traps, but at the same time, you have less number of carriers. So what you have here is that your photocurrent drops because your effective trap density has decreased, and your speed also your speed improves. So you don't see as much of persistent photoconductivity that you see when you have when you have, for example, the supported RES2 device. The third case is when you have a suspended device and now you turn it on. Now you fill some of these traps. There are less traps, but you fill some of the intrinsic traps with these carriers because of the gate voltage. And so you now see a further drop in the photocurrent. So you can see the photocurrent has dropped now to about 150 nanoamps. And you see faster switching. So you can see that when you pulse the laser on and off, like in plot K, you can see faster switching here as compared to what you saw when you have a large number of unfilled traps, as in plot I. And then finally, when you have the supported device and you turn it on completely, a full gate voltage, then you start seeing that your photocurrent drops even further. You have almost completely filled the traps here with the gate voltage induced carriers, and you see fast switching, but you don't see a large photocurrent. So what I'm trying to show you here is that as you decrease the effective trap density, you see increasing speed, but you lose photocurrent. So qualitatively, you can see there is a trade-off between responsivity and speed. You can modulate this at higher frequencies. When we do higher frequencies, at 10 kilohertz, then we start seeing response times of the order of microseconds here, but we don't see a major difference between the supported and the suspended device. If you look at the bottom two plots, you can see that you can move from a photogating regime into a photoconduction regime, either using gate bias, so by filling up traps, or you can use the effect of a reduced trap density in the case of the suspended device to move from photogating to photoconduction. You can estimate the traps using simple IV curves, and you can see how the impact of effective traps here. So you're plotting response time versus effective trap density. You can see that as the trap density changes, your trap density decreases, your responsivity decreases, and your speed improves. So your responsivity goes down to 0.5 amps per watt, but your speed has now improved to 10⁻⁵ seconds. So to illustrate a basic trade-off in responsivity and speed. Now, if you come back to the same plot that I had shown earlier, and we put this data on this plot, what we see is that you can modulate. Again, we don't have great numbers here, but what you see is fundamentally you can modulate between high R and high speed by modulating the effective trap density in your device. So you are somewhere on this curve. So the next point was, how do you break this trade-off? How do you change this trade-off between responsivity and speed? So that brings me to my second piece second device that I wanted to illustrate. So we want to see how we can engineer the responsivity and speed in WSE2 phototransistors through a lateral PN junction. So what do we do here? We create a slightly different kind of device. So what we have here is a WSE2. So what the pink here is a middle gate, and then you have two side gates. So it's a 3-gate device. There are two side gates, and there is a middle gate, and you have WSE2 and HBN on top, and you have source drain electrodes. So the device actually looks like this. So you have a middle gate, and you have two side gates, and you can use the two side gates to modulate the lateral field in the device. So you can modulate it from being an NPN device to a PNP device in this direction, in the perpendicular, in the transverse direction to the source drain direction. So this is a few layer WSE2 flake, and I'll show you how we can use this lateral side gates to modulate the responsivity and speed trade-off in this device. So the fabrication is fairly simple. You start with an SiSiO2 wafer. You pattern these gates, then you transfer HBN, and then you transfer WSE2, and then you make these contacts. And what I'm showing you here is a cut across the main channel of the device, which is AA prime. Now, if you look at the dark current voltage characteristics, you see a nice ID. It's a P-type transistor. So you see a hole conduction here. And then if you apply the side gate voltage, so you vary the side gate voltage, you can vary the dark current here. So your orange is the no side gate voltage, and then the side gate voltage moving up and down is where you can modify the dark current. So you can see here in this band diagram taken across this device, you can vary it from being to a complete NPN structure here when you make the side gate voltage 0.5 volts. And we have verified this by also measuring the current in the transverse direction, and we see a PN junction being formed between the middle WSE2 and the side WSE2. So we have done that check also. Now, so you see an increase and decrease in the dark current. Now, what happens when you start illuminating this device with light? So if you look at the photocurrent with the, this is plotted versus the middle gate voltage, and what you have here is you're modulating the side gate voltage. You see a modulation of the photocurrent. So here also you can modulate the responsivity by modulating the side gate voltage, and you can modulate it from being less to high, and you can go down and up. And that's because you are creating this field within the device, which is separating out the carriers. And so, for example, when you apply a side gate voltage, which is a positive side gate voltage, at the bottom, you can see this NPN diagram. You're emptying out electrons from the middle channel, and you are filling it in with holes from the side. And so, you are essentially enhancing the whole population and decreasing the electron population. That's going to enhance your overall responsivity, and you are also you're going to decrease the recombination rate here because of this change in population. And remember, you're not relying on traps now. You're relying on changing the photocarrier population using side electric field rather than traps. So, and we see that evidence when we plot the photocurrent versus laser power, that we have less effective trap density when we look at the positive side gate voltage, the +2 volts here, for example, compared to the no side gate voltage, which is the orange. So if you look at the temporal photoresponse, how does the speed change? Now, if you take the conventional device, which is the middle gate, which is the middle channel, where you see a standard conventional response. So you're when the channel is on, which is at -0.5 volts, you have high responsivity and slower speed, and when your channel is off at 0.4 volts, you have lower responsivity and lower speed. But what happens when you apply the side gate voltage? So I'm plotting the responsivity versus speed here for this device, and what happens when you apply the side gate voltage? When you apply the side gate voltage, you are essentially injecting electrons into the middle channel, injecting holes into the middle channel and emptying out electrons. So what you see is that you have seen an enhancement in responsivity without a reduction in speed. So your responsivity versus speed trade-off actually becomes better. You are getting a slope of 9.8 here as opposed to a slope of 4. For the conventional device. So what I'm trying to show you here is that by using the side gate voltage and modulating the population of carriers inside the channel, you can change this basic trade-off between responsivity and speed. So essentially, you're enhancing responsivity by putting in carriers into the middle gate channel without taking the help of traps. And this will translate into an effective gain. So you can see that the photoconductive gain, for example, you see on the left-hand plot, your gain is now going from 120 to 280 without much change in the lifetime, whereas your gain doesn't change much if you're only relying on the middle gate voltage. So conventionally, your gain only changes from 188 to 2202, whereas with the side gate voltage, you see a much larger change in gain. So essentially, you're gaining a lot of responsivity without sacrificing speed. The external quantum efficiency does not change much. And there's another impact. We see an improvement in the overall noise and detectivity. So for example, if you look at the noise performance, and in these devices, it's essentially the flicker noise that dominates instead of short noise and thermal noise. If you look at the flicker noise and you see how so the solid lines here are without the without the side gate voltage, and the dotted lines are with the side gate voltage. You can see that the noise floor is lower when you apply the side gate voltage, and this is essentially because your dark current actually drops. When you deplete the channel from the side, your dark current drops, and you see an improvement in noise. So this noise improvement translates to an improvement in detectivity. and you see an improvement in detectivity because of the change in improvement in noise. And when we try to switch the laser on and off at 0.20 at very low powers, this was just a small experiment that we did, we can detect the laser power of 0.25 picowatts also in this device with the side gate voltage on, and we don't detect it without the side gate voltage. So clearly the side gate effect improves the overall detectivity of the device also. So there's an enhancement in responsivity and there's an enhancement in detectivity. And now we come back to the same plot. And where are we on the same plot? So this was our older device, and now this is a newer device, which clearly shows that you have improved responsivity without sacrificing much of speed. So you are now somewhere here. And if you benchmark this work against the three main parameters of detectivity, speed, and responsivity, then you're now starting to push towards this corner of the desired corner by high detectivity and fast speed and high responsivity. So now I'll finally talk about my last piece of work. I don't have much time, so I'll quickly go through some recent work where we try to engineer a heterojunction. And I'll tell you what the basic idea here is. So we try to make this RES to WSE2 heterojunction. Heterojunctions are also another way to engineer optoelectronic performance and really relies on the hetero interface. This is the heterojunction. It's a type 2 heterojunction. If you draw just the band diagram, it's a type 2 heterojunction. But the more interesting thing is when you start doing the band structure calculations. If you do the band structure calculations for multi-layer WSE2 and RES2, you start seeing the emergence of a near direct band gap at the interface. This only happens when you have multi-layers. You don't see this in monolayer. So when you have multi-layer, you have this indirect band gap at 0.68 eV, but you also see a very direct band gap at around 0.7 eV, which we believe and leads to an enhancement in the photo response. These are some of the calculations. I'll not go through a lot of that. But let's look at whether we do form a type 2 heterostructure or not. So when we look at the PL data for various devices at room temperature and at low temperature, for few layer, 8 layer, 2 layer devices, we see that the PL gets quenched at the hetero interface. So we confirm that it's type 2 band alignment. And we also see an IR response. So we see that although this the hetero interface, the two materials are not supposed to respond in the IR region, we see that we see an IR response because of the hetero interface. So it also confirms this type 2 band alignment between WSE2 and RES2. And now when we start looking at responsivity and speed, we start seeing numbers which are modulated here depending on the thickness, but of the order of an amp per watt here, and detectivity of the order of 10 raised to minus 10 raised to 10, 10 raised to 10 to 10 raised, yeah, about 10 raised to 10. And when you look at the speed, again, we see that the speed is of the order of microseconds, and it depends on how thick your devices are. The few layer devices are faster than the thin devices. And again, when you plot the responsivity and the speed as a function of frequency, you see that the responsivity drops at high frequency. This is whereas the speed and the speed improves at when the responsivity drops. It's the similar trade-off that we see for responsivity and speed in the device. But what is interesting is that once you have a heterojunction, you can also start seeing a photovoltaic effect because of this internal electric field, and we see a fairly large open circuit voltage because of this interface, which is about 0.64 volts. So we see a very high VOC of 0.64 volts. So coming back to my last slide here, again, if I go back to the same plot and plot my three pieces of work. So this was the original device. The WSE2 lateral PN junction is right here, the star. And then now as we make this heterojunction, we start pushing the speed further down because of the hetero interface. And then we also get the benefit of a large VOC and ISC because of the PN junction. So To summarize, 2D layered TMDs offer rich possibilities to optoelectronic physics, role of traps in photodetector performance, and you can also figure out ways to modulate the optoelectronic performance using heterostructures or electrostatic modulation that I just showed you in the previous two examples. And I would like to acknowledge my students, the IIT Bombay Nanofabrication Facility, and sponsors of this work from the government and industry. With that, I would like to thank you, and I'm really sorry I overshot the time.
Okay, thank you, Professor Lodha, for a very nice talk. Now the session is open for the questions. I think we have, we are running out of time, so maybe we can address one or two questions and then we can move to the next talk. Yeah, is there any question?
Yes. Hi, my name is Krishna. Professor Lodha, could I ask a question?
Sure, yeah, please.
So I have a very probably a very simple question. So when you talk about the effect of traps on photodetectivity, when you compare between layers on an insulator and suspended, is there a dependence on the dielectric environment the material is on? Like when comparison with the air and the substrate, does it affect the excitonic properties of the material? Does it change, let's say, the Coulomb interaction between the particles? Does it change the lifetime and such?
So I think that's a very interesting question, and I think it will surely have a big impact. The environment has a big impact on the performance. To give you an example, so for example, in our device, the one that I showed, we had the suspended device and we had the device on the SiO2. But the problem there is that the gate voltage is also far away. So the capacitance change is also convoluting the data. But in general, for example, if I take HBN instead of SiO2, we have seen in our group that if you take HBN, we get much better performance. And HBN is a 2D material. And the interface is much cleaner when we use HBN as compared to SiO2. So you're right. So the performance is highly dependent on the interface and the dielectric that you form with the interface.
Right. Thank you.
Sir, can you switch to slide number 32? I have a question over there.
Yeah.
So in the IDVD plot, why there is drop in current at VG minus 10 volt specifically, or there is error?
Let me see, 0.
0 volt drain current is higher than minus 10 volt.
Guess 20. Yeah, so I think we don't see a very So I think that's the drop at near zero bias, right?
Yes, sir.
I think what you're seeing here, if I'm not wrong, is more. So you see that there is a slope there is a larger slope to the reverse current. I think that you're seeing more of a tunneling effect here rather than a thermionic current. And I don't know exactly whether this is a real signal in terms of the drop here, or whether repeated. It's almost the same as at 0 volt. So we don't see I would say we don't see a big difference between minus 10 and 0, and we start seeing the current going up only at minus 20 and so on.
But in the positive drain bias range,
oh, you're saying positive bias.
The current is very much higher.
Positive bias. I'm not sure. I'll have to check.
Okay, sir.
Yeah, I'm not very sure.
And sir, second question is that based on the recombination and transit carrier time lifetime. So have you compared with this heterostructure in the suspended form? How do you see that?
No, we have not made a suspended heterostructure. Sorry,
okay.
That's a tough task. I haven't tried a suspended heterostructure yet, although I have seen some reports of papers with suspended heterostructures, but we have not tried anything like that.
And sir, last question, how do you see this lateral as well as side gate with respect to recombination the carrier lifetime. How that affect that, or how do that improve?
Okay. So for the side gate data that I showed, the lifetime depends. So as I said, right, when you change the side gate voltage, you're essentially changing the gain of your device, and which basically means that you're changing the lifetime. So the lifetime essentially gets enhanced because of the side gate voltage, in a sense, right? Because it appears as you're changing the carrier population, so you're enhancing the responsivity, you're enhancing the gain, and hence you're essentially enhancing the lifetime. So the side gate voltage effectively does that to the photocarriers in the channel.
Okay, sir. Thank you.
Okay, so I think with interest of time, I think we should thank all the invited speaker for the very nice talk, Professor Gomez and Professor Lodha. And we'll have a lot of questions, and we can send them emails and ask questions if we have further questions. And if we have time left, we can again have a discussion session after these talks. So, okay, so thank you, Professor Lodha, for a very nice talk, and I'm sure that we'll have a lot of questions and we can get back to you. Okay, so with that, I think we'd like to now start the next talks, which are the oral presentation. So the first oral presentation is by Mr. Shaheen Sharifi from IIT Delhi. Title of his presentation is High Temperature Performance of a gallium selenide nanosheet based broadband photodetector. Hello, Sain, please go ahead. Sain, we cannot hear you. Hello? Please unmute yourself, and yeah, think we are not able to hear you. Okay, I think you are muted. Please unmute yourself.
Okay, now I think it is muted.
Yeah.
Okay.
So you have 15 minutes, so you can please start.
Okay, now is everything okay? Should I start?
Yeah, please share your screen.
Yeah, now is it visible? Should I go ahead?
No, your screen is not visible.
Okay, just give me some seconds. Okay. Is it visible now?
Yes.
Okay, so I'm starting?
Yeah.
Okay. Okay, so my name is Shaheen Sharifi, and I'm a PhD research scholar at Indian Institute of Technology, Delhi. And my title of this talk is High Temperature Performance of gallium selenide nanosecond Gorgon photodetector. So here is a brief outline of my talk. So firstly, I will introduce about the material, then it will be followed by some literature survey and information, result and discussion, conclusion, acknowledgement, and finally we'll end up this session with giving references. So dimensionality, dimensionality is the one of the most defining material parameters. The same material can exhibit different properties depending on whether it is arranged in 0 dimension, 1 dimension, 2 dimension, or in 3 dimension. So in 3 dimension crystal structures. Among the crystal structure, my interest lies in 2-dimensional structures. So what is a 2D material? So the materials in which the atomic organization and bond strength along 2 dimensions are quite similar, but much stronger than along 3rd dimension. Now, the journey of exploring 2D materials began with the work of Novoselov and Genome, Novoselov and Gaim with the work on graphene in the year 2004. But graphene has a lot of good properties, good carrier mobility of the order of 10 to the power 6 centimeters square per volt second. But because of its zero band gap energy, its application in various fields was restricted. Therefore, several attempts were made to synthesize new material which can overcome this restriction. And it includes insulating HBN 2D materials and 2MDCs, tensile metal dichalcogenides, MX2, like MOS2, WS2, T, WSA2, etc. Now, initially, most of this research work was confined in these TMDCs because TMDCs shows very promising in the field of photo detection. Now, recently, scientific community is chasing for metal monochalcogenides, MX, like gallium sulfide, gallium selenide, indium selenide. So I'm working on these monochalcogenides, and among these, I'm working especially with gallium selenide. Now let me just tell you about gallium selenide. Gallium selenide is basically a 3-6 semiconducting layered compound, and each monolayer of this semiconducting compound is around 8.8 nanometer thick, consisting of atoms, 4-atom sequence of selenium, gallium, gallium, selenium. And this gallium selenide has a direct band gap of 2 electron volt in the bulk form, but when it is thinned down to monolayer, it can go up to 4 electron volt band gap. And its crystal structure is hexagonal, and I have shown some of the properties of this gallium selenide in this table. You can see now the bond in the interlayer plane of this material is strong covalent, but the bonding between the interlayer plane is weak van der Waals, and that helps us to cleave this layered material into different layers. We can easily utilize mechanical exfoliation to cleave this material in layers. Now, gallium selenide has got several applications in different fields, like it is used in visible and UV photo detection, non-linear optical application, terahertz source generation, etc. Among these applications, I am interested in UV pitch photo detection. Now, I have done some literature survey. So here I am just highlighting some of them to highlight. So firstly, Novoselov et al. Used this mechanical exfoliation method or the Scotch tape method to obtain few or even single layer graphite or graphene. So you use that idea because our material is also a layer material. So we can also use the same technique to extract this material in different layers. Now, Jufan et al. Deposited this material using controlled vapor phase method, and they observed some of the interesting properties, like the Raman peak shows shift with the change in layer numbers. If using mechanical exfoliation or any other method, if the layer number is changed, the Raman peak showed some shift. Gallium selenide demonstrated a direct to indirect bandgap transition when thinned down to monolayer from its bulk counterpart, which is exactly opposite that of the TMDCs. In case of TMDCs, it is indirect in bulk form, but it becomes direct when it is thinned down to monolayer. And Jufan et al. Fabricated a device on this, and they got a responsivity of 1.7 ampere per watt. Next, Ping An Hu also deposited device on a few layer gallium selenide, and they incident photon on it, and they observed that when the gallium selenide based photo detector is exposed to shorter wavelengths of light, it shows higher photo responsivity. They got a photo response of 0.02 second from their device. They got a high photo responsivity of 2.8 ampere per watt, and they got high external quantum efficiency of around 1367% at 254 nanometer. In this table, here in this table, I have shown you some of the properties of 2D nanostructure photodetector. We have compared some of the parameters. It is taken from this literature, and from this table we can clearly see that this gallium selenide has a strong potential to act as photodetectors. And finally, I would like to highlight one more paper. So in this paper, PLG et al. Showed that the properties of the photoresponsivity of gallium selenide based photodetector strongly depends on the thickness. So they have they have made 4 devices of different thickness, and they show that when the device is thin down from 72 nanometer to 32 nanometer, the order of photoresponsivity decreased to around third order. So firstly, so this is my motivation. So most of the research work beyond graphene was limited to MOS2 and other TMDCs. Only little work was done on monochalcogenides like Indian selenide, etc. Now recently, a few nanoelectronic and optoelectronic devices based on this monochalcogenides have been fabricated, and they show promising potential in application of nanoelectronics and optoelectronics. Especially gallium selenide is promising for photodetection because of its low dark current and high one-off ratio. And most electronic transport and optical properties of gallium selenides are quite sensitive to external conditions, which are very interesting to explore. And it can well incorporate different doped elements like sulfur, aluminum, etc. So my results are divided into 5 parts. Firstly, transfer of this gallium selenide flakes, then surface analysis and thickness measurement, then optical characterization of these flakes using Raman and PL, photo detection measurement on the as fabricated device at room temperature, and we have also observed the photo response behavior at high temperature. So these are some experimental techniques which I have used in fabricating the device and characterizing the device. So mechanical exfoliation, optical microscope, EM lithography, thermal evaporation, probe station, and semiconductor characterization system. So as you can see, this is one of the flake of gallium selenide. So we procured this two-dimensional, we procured this gallium selenide crystal from two-dimensional 2D semiconductor. And you see it is a little bit reddish in color, it's very fragile. And as it is available in layer form, we can easily cleave it using the mechanical exfoliation. We use mechanical exfoliation because it gives high crystalline quality of gallium selenide. The transferred flake ranges from a few microns to few tens of microns, and we get we get flakes of different thickness. Now, as you can see, some marks are shown here. Now, exfoliating gallium selenide flakes and choosing for suitable flakes, it's quite inefficient. That is why we made some marks, metallic marks, using electron beam lithography and thermal evaporation, so that we can easily identify our desired flake. Now we use AFM technique to estimate the thickness of the gallium selenide flake. Here, the morphology of this flake has been shown, and a height profile has been drawn corresponding to this dashed line, and we got to measure the thickness of this gallium selenide flake to be around 26 nanometer. And thickness of the gallium selenide flake was almost uniform. So we then did PL measurement to estimate the band gap energy. So we got a we got a peak corresponding to the band gap emission of gallium selenide, which is obtained at 620.5 nanometer, which correspond to a band gap energy of 2 electron volt. Later on, we did Raman measurement, and in the Raman measurement of gallium selenide, we see 3 dominant peaks. 2 of them are out of plane, A1G1 and A1G2, and 1 in plane mode. So 3 dominant peaks, and in addition to these 3 dominant peaks, we also got 2 another peaks. So one peak, there is a small soldier at the high frequency end of this A1G1 mode, this peak, and a broad feature of amorphous selenium, which is positioned at around 249 centimeter inverse. In this figure 2, we have shown the displacement of the gallium and selenium atoms in the 3 dominant Raman active modes of hydration. Now here I have shown the detailed process flow for the device fabrication. Firstly, we clean the silicon substrate using acetone IPA. Then we have grown thermal oxide SiO2 of thickness around 300 nanometer. Then we fabricated marks so that we can easily identify our gallium selenide flakes. Then after depositing these marks using EBL and thermal evaporation, we exfoliated our gallium selenide flakes onto them.
Shine, you have Shine, sorry for interruption. You have 3 more minutes to for the talk.
Okay, so then metallic contacts are deposited on this gallium selenide flakes, and we got our device. So this is the ACM and optical images of this fabricated devices, and I have also shown you some of the parameters. Now let me just tell you how does this device work. So this device is basically a MSM device, and it's basically two Schottky barrier connected back to back. So when we apply voltage across these two contacts, one contact becomes forward bias, another contact becomes reverse bias, and electric field is established, which helps to separate the charge carriers. Now when the photons are incident on it, electron hole pairs are generated, and because of this electric field coming from the applied voltage, the electron hole pair gets separated and we get photocurrents. So firstly, we did photoelectric measurement on our device. Firstly, we measured our dark current in this range -5 volt to 5 volt, and we illuminated our device with 620 nanometer laser light, and we see an enhancement in the current. Later on, we varied our wavelengths from 650 nanometer to 220 nanometer to record the spectral response, and we see our device shows a responsibility of around 790 milliampere per watt in the visible range and around 1300 milliampere per watt in the UV range. So gallium selenide based photodetector can be utilized in both UV and visible region. We also did power dependent photo responsibility using laser light of 370 nanometer. It has been plotted here. We see the when increasing power, the responsibility decreases because responsibility is inversely proportional to the power. So at a minimum power of 0.07 milliampere milliwatt per centimeter square, we got higher responsibility of 2.5 ampere per watt. Next, we take the measurement of our fabricated device by varying temperature. We vary the temperature from 27 degrees centigrade to 120 degrees centigrade, and we see the dark current as well as the photocurrent got increased. Now, in the elevated temperature, dark current increase, dark current also increased, photocurrent also increased, but the PDCR value, photo to dark current ratio, it got decreased because the increase in dark current was more prominent than the increase in photocurrent. Now, as dark current and photocurrent both got increased, so that effectively gives photo responsivity of 4.5 ampere per watt at 120 degrees centigrade. So from here we can conclude that our device maintains photo response and thermal stability up to a high temperature of 120 degrees centigrade. Even at high temperature of 120 degrees centigrade, it gives us high photo responsivity of 4.5 ampere per watt. Okay. So I would like to acknowledge my supervisor, Professor Icee Singh, for his continuous support. And I would also like to thank our research members, all the colleagues of my lab, Department of Physics and NRF, and Professor Binay Gupta, Professor Monica Thoma, University of Delhi. And I would like to thank DST for providing me research fellowship. And these are some references which I have used in making this presentation. Thank you.
Thank you, Shine, for the very nice talk. So if there is any question in the audience, please ask. Okay, so if there is no question, maybe I can ask one question. So, Sahin, have you characterized the contacts? So, what is the effect of, for example, the Schottky contact on your photo detection devices?
So, will you repeat some bit?
The effect of Schottky contacts on your devices. Have you characterized that?
No, sir, I did not characterize till now. I have it in my future plan. I will do that.
Okay. Okay, so if there is no more questions, maybe I can Hello, Naveen, are you there?
Yes, sir. Am I audible?
Yeah, so please, sorry, I was muted at that time. So Mr. Naveen from Beats Pilani, Hyderabad. So his title of the presentation is Fabrication of Few Layer SNS2 based flexible pressure and strain sensor and understanding the transaction through first principle calculations. Please, Naveen, please go ahead.
Thank you, sir. I hope my presentation is visible to everyone.
Yes.
Yes. So, good afternoon to everyone. Myself, B. Naveen. I'm a research scholar from BITS Pilani, Hyderabad campus. Today, I want to present a paper titled Fabrication of Few-Layered SNS2-based Flexible Pressure and Strain Sensor and Understanding the Transaction through First Principle Calculations. So, coming to the introduction, the flexible sensors have captivated a lot of attention due to huge demand for futuristic electronics. However, there are different types of flexible sensors are present, out of which the strain and pressure sensor are gained a lot of attention due to used in different applications like robotics, health monitoring, and e-skin applications, and etc. The piezoelectric and piezoresistive, piezoelectric and piezoresistive and capacitive mechanisms are the heart of such a sensors. However, most of the reports not explored the transduction mechanism, I mean physical transduction mechanism of such a sensors. Only few reports are explored. It is a good to understand the physical transduction mechanism for better understanding as well as optimization of the system. So the one method is used for understanding such a type of physical transduction mechanism is a DFT, density functional theory. So what is density functional theory? So density functional theory generally basically describes the properties of a matter, for example, molecules, nanostructures, surfaces, and interfaces. As you look at this image, we are basically giving the lattice structures to the system, which will perform some theoretical calculations and analyze it and gives the result in the form of density of states and energy band structures, etc. So in order to fabricate such a flexible pressure and strain sensor, there are different materials are considered. For example, if you look at this left side image, there are substrates used for flexibility and electrodes used for the signal carrying and active materials used for sensing different stimuli. So with the advent of graphene, 2D material graphene, the research is interested to explore new different types of 2D materials in which the transition metal dichalcogenates gained a much popularity because of its exceptional properties. And these properties can be tailored with different synthesis methods by controlling the size and changing precursors. And one of the advantages is we can tune the TMD's band gap by changing the bulky TMDs to mono layer TMDs. I mean indirect band gap to direct band gap. So as you can see here, the TMD is a layer structure with different phases like 1T, 2H, and 3R. However, these TMDs electronic properties are very sensitive to external stimuli like temperature, strain, and pressure, etc. So, tin disulfide is one of the transition metal dichalcogenate material which has excellent electronic properties, and it is one of the layer structure as you can see in this image. Tin
atoms are sandwiched between the two dichalcogen atoms. The main benefits of using the SNS2 is we can tune the band gap of SNS2. It is useful for different sensing applications, as well as it is a earth abundant material. So because of that, because it makes the low cost, and it is a well alternative to the other TMD materials called MyS2 and WS2, etc. So apart from this, different TMD materials, SNS2 are least explored in the physical sensing mechanism. So the fabrication of SNS2 based pressure and strain sensor. So here we are not using the CVD technique because of its due to high temperature constraints and very tedious process to transfer functional material to the flexible substrate. Instead of that, we are using the hydrothermal method for synthesis of SNS2 because of its facial and cost effective and suitable for large growth area and high temperature growth also. So in brief, we take tin chloride and thiolate added to the water and later sonicated for 15 minutes to get the transparent solution, and this transparent solution is transferred to the hydrothermal method, sorry, hydrothermal reactor for 7 hours at 200 degrees centigrade, later followed by the natural cooling. So after getting the solution, we centrifuge it for 30 minutes in order to remove any residues from the SNS2 liquid. So finally, the yellow powder is formed at the bottom of the tube, as you can see here. So this liquid is deposited in the cellulose paper by using the vacuum filtration method. So once the vacuum filtration method is done, this cellulose paper is dried for 80 degrees for 20 minutes. So after cutting into the required dimensions by using the solution casting method, we are fabricating the pressure and strain sensor. So here we are using the PDMS for that because of its flexibility. And finally, the fabricated device is. So in order to confirm the synthesized SNS2 on the cellulose paper, we perform different characterizations like XRD, XPS, and Raman spectroscopy and FESM. If you look at the figure A, all the peaks readily indexed to the hexagonal structure of SNS2. And similarly, if you want to know the chemical and oxidation states of the SNS2, the XPS analysis performed, where it is clearly showing the XPX spectra, the SNS2 is formed. However, there is an oxidation peak is observed because our sensor is partially oxidized. And to further confirm the SNS2, the Raman spectroscopy was performed. However, we observe the two prominent peaks. One is the easy peak in plane and the other one is the out of plane peak. So finally, we perform the FESM to understand the morphology. Here we look at this semi-mesh. The grown SNS2 is a microflower structure, which each flower contains individual narrow structures. However, it is a percolating medium. So we investigated the pressure and both strain sensing properties by applying different pressures and strains to the fabricated device. Initially, we applied different pressures and we observed that there is a linear change in the current was observed, as you see in the figure A, which indicates that the fabricated sensor is a piezoresistive type. And similarly, different constant pressures and increasing pressures are applied to the fabricated center and observed that there is a change in the current was observed. And one of the important parameter for a pressure sensor is a sensitivity, they calculated to be 106.83 kilopascal inverse. And further, the fabricated center is subjected to 1000 pressure cycles, and we observed the negligible change in the performance was observed. And one of the most important parameters for the present sensors is time rate, rise time and calculated to be 420 milliseconds, and fall time is 320 milliseconds. The similar experiments are carried for the both for strain sensing also. Here we applied both compressive and tensile strain. We observed that there is an incremental change in the current for compressive strain, and there is a decrement in the current is observed in the tensile strain. And one of the important parameters for strain sensor is gauge factor, which is 22.83. So it is worthy to note that the calculated sensitivity and strains are better compared to the other sophisticated fabrications of pressure and strain sensors. So the underlying mechanism here is, which means by changing the current by applying the different type of stimuli, is ascribed as when you apply pressure or compressive strain to the fabricated sensor, the distance between the nanoflakes will decrease and ultimately leads to the increase in the current. The similar mechanism applies to applying tensile strain. Here, by applying the tensile strain, there is an increment in the distance between nanoflakes was observed. Thereby, which will decrease the conductivity.
Naveen, you have 3 minutes left.
Oh, okay, sir. Okay, sir. Conductivity. So, this is the qualitative analysis. In order to understand the transaction mechanism, in order to understand the transaction mechanism of different stimuli acting on the sensor, we used first principle calculations with the help of atomics toolkit and virtual nano lab, which is provided by the Synopsys quantum wise simulation package. Here, in order to understand the electronic properties, first we have to optimize the geometry of the SNS2 structure. So for that, we considered three-layered SNS2 configuration for both pressure and strain, and these configurations are geometrically optimized using the LBFGS method. And further, it is optimized by using the local density approximation and Predew-Junger-Exens correlation function. Here, LDA is not used for the calculation of electronic properties of the material because it severely underestimates the band gap. So for calculating the electronic properties, we use the meta-GCA method with Transpo-Exens correlation function, which is the improved versions of Becker-Johnson and Exens potentials and LDA correlation potentials. And finally, the vacuum of 40 Armstrongs is considered in out of plane direction to avoid the artificial interaction from the periodic images. And finally, the obtained band structures for the different strains and pressures, as you can see here. If it is initially the band gap of the sensor is this one. By applying the different strains like pressure and strain, we observe that there is effective change in the band gap or as well as in the effective mass. In the case of compressive pressure, we observe that there is a change in the band gap. But coming to the applied strain for the compressive strain, the change is in the effective mass. And it's similar for tensile strain, there is an increment in the effective mass. From this, we can conclude that applications of strain and pressure modulated both band gap as well as effective mass of the modulated the effective mass of the material. So finally, my conclusion is both band gap and effective mass affects the conductivity of the material. So finally, the conclusion is that 2D SNS2 thin film was deposited successfully on a cellulose paper, and SNS2 film deposition of cellulose paper was confirmed using the various characterizations, and present strain sensors So the SNS2 film is optimally utilized for presence sensing as shown excellent characteristics, and band gap and effective masses affects the connectivity SNS2 is found by using first principle calculations. I would like to acknowledge my funding that is Bits Pilani Hyderabad, SEB, and Red Pine Signals. Thank you.
Okay, thank you, Navin. Is there any question? Please go ahead and ask. Okay. Okay, so I think we are also running out of time. So I think we are 10 minutes late. And maybe I can ask a quick question to Navin. So Navin, so this SNS2 film, so you obtain it by liquid exfoliation, is it?
Yes, by hydrothermal method.
Okay. And any idea about how many layers you are depositing on your device?
Sir, actually, by using the Raman spectroscopy, we can find out how many layers. In this, the gap between the in-plane out-plane was almost 105 centimeters. So, which can conclude that it is a tri-layer device.
Okay. Okay, thank you. So, if there is there any other question? Okay, so if not, then we thank the speaker. And also, I'd like to thank all the speakers for this session, both the invited speaker and the oral presentation speakers. And maybe the next session is the poster session. So I'd like to ask Ankur and what basically you would like to do now before we go to the next session. So it is over to Ankur now.
So thanks, Professor Dhara, regarding your session chair, and it was very nice presentations by all participants. So we'll have now e-poster session. E-poster session is basically presented by all the participants which are given in the Icee 2020 link, and we would like our volunteer Sumit is around here, or so they have the list so that we can present in the same hall. If the authors are actually the author supposed to present here online, the e-poster will be presented here and they will present their brief 2 minutes talk on that. So that is being hello.
Sorry to interrupt, but
okay.
The schedule is Hall 3 is for Flexible Electronics Symposium, and we are already
3:30. Okay.
supposed to start at 3:30.
Okay, I think the e-post. Okay, thanks. Okay, then we'll meet at 5 o'clock. Okay, fine.
Okay.
The e-poster is online, and the judges can go there and then listen, watch the poster and give their feedback. Okay, thanks a lot. So over to Madhusudan Singh, Professor Madhusudan Singh.
Thank you.
Yeah.
So I apologize for the late start to the poster session. So we were supposed to start at 3:30. So we will go on until 5 o'clock, which is the scheduled time, because at that time we have a invited lecture by Professor Guo in Hall 8. This changing of hall business is actually is causing a little bit of logistical problem today. So let's get started. Ritesh, please take over at this point. And you can visit any poster that you might. Yeah.
Yes, sir. So basically, I'm going to share my screen in which from poster number 84 to poster number 100 will be there. So I will be spending almost 2 minutes approximately on each poster for a single poster. And if any presenter is there for that particular poster, he or she can present his poster within the 2 minutes. So I am just sharing my screen, just a minute, with poster number 84.
Hello.
Yes, yes.
Audible? Yeah, can I start?
Yeah, this is your poster, then yeah, then you can start presenting.
Okay. So, good afternoon, everyone. I am Nitish Nair, an interdisciplinary research scholar from the Department of Metallurgical and Materials Engineering and Electrical Engineering from IIT Madras. And today I'm going to present some of the simulation works. That's something I recently learned simulations because of the pandemic conditions I forced to sit in home. And I'm discussing about transparent touch sensors. So basically a touch sensor is something we commonly used in our mobile phones, which is installed on top of the display and hence it need to be transparent. And I fabricated it using printed techniques, so which make me to restrict my dimensions to two dimension. So I implemented an interdigitated touch sensor, which actually consists of a set of electrodes, which is printed over a PET substrate, and a PDMS layer is coated on top, which will act as the dielectric as well as the protective coating. So when I touch on top of the display using my hand, it's actually a highly absorbing material of 60 to 80 permittivity, and which in effect acts as a ground, which will absorb the fringe field which is present between the electrodes. And because of that, there will be a change in capacitance happens. So this change is used to detect a touch. So I performed the experimental and implemented touch sensor and observed that the simulations are quite matching with the experimental works. So my main focus of the simulations is to understand what happens or how it behaves if I perform a bend or a flexibility to the device. So mostly if I bend, its performance varies basically because of variation of the resistance, which may be because of a crack formation, delamination, or local stress produced, or it can be a capacitive variation. So in this work, I focused on silver nanowire, which is a material of highly flexibility, and hence I can neglect the resistance variation. So I kept a plot of a bending test I performed using silver nanowire experimentally, which shows that the maximum variation in resistance is below 20% even after 10,000 bending cycles. So I can neglect the resistance variation. And the other possibility is the capacitive variations, which could be purely geometrical. So I try to learn how the device behavior varied with bending. So by bending the sensor in A dash and B dash directions, obtain the optimum dimensions along which the variation or sensitivity is minimum. And using that dimension, I fabricated a sensor, which is shown in the image slash. And if you want to see the working, you can scan the code. And I fabricated a touchpad, which actually corresponds to which position you are touching. You can see an LED is glowing. So in effect, I used a simulation technique to understand the behavior of the device and how I can optimize it for better performance under stress conditions, not stress, bend and flexible conditions. So yeah, if you have any questions, feel free to ask, and you can mail me also in my mail. Thank you.
Is there any questions? Okay, then I thank you, Nitish Nair, for presenting the poster. Now we will be moving to the next poster.
Thanks.
Yeah, this is poster number 85 by Vaibhav Rana. Is Vaibhav Rana here? Okay, then if he is not there, then I am just scrolling it down so that the people can have a look on this poster. As the presenter of the poster is not here, so if attendees have any question, you may note down his email ID so that you can directly communicate him and ask for your doubts. So we are moving towards the next poster. This is basically poster number 87. Poster number 86 is not available with us, and we were informed that the poster is not submitted. So this is poster number 87 by Kamlesh Tripathi from Icee Bhopal. Is he there online?
Yes, am I audible?
Yeah, you are audible. I am giving you 2 minutes. You just start and just presenting.
Okay. Good afternoon, everybody. I'm Kamlesh Tripathi. I am doing PhD in Icee Bhopal in electrical engineering computer science department. Here, actually, we are when we are using any flexible electronic devices, there the main concern is how the bending, stretching, twisting, and other mechanical deformation affects its lifespan, and also how its uh, electrical behavior changes. Here I use COMSOL multiphysics to simulate a substrate of PEK, that is polyether ether ketone, which has outstanding mechanical, electrical, and thermal properties, which can be used as a very good flexible material. Here we are giving its cyclic deformation or loading to know how stress and strain develops all over its body, and its fatigue life means how much cycles of loading it can take with stable operation. Now here with COMSOL multiphysics 5.5 we did this simulation. Now we used here SWT model, that is Smith-Watson topo model, which generally used to calculate fatigue life of a metal fatigue for its fatigue analysis. Generally, uh, all the models are used in metal ductile materials. We can use it for flexible material polymers to see how it works, and we can verify which model will give accurate result experimentally. So now here as the figure shows here, we first in figure 1a, we discuss we are showing here how the von Mises stress develops. The stress and strain pattern is more, the magnitude is more in the middle, and gradually it decreases to its sides. Another thing is when we are bending the convex side, that here it's the bottom side, and concave side which is the bottom side, and the convex side which is the top side. So in
Please
concave
conclude quickly.
hello.
Please conclude quickly.
Okay. Actually, the tensile strain develops in convex side, and the concave side, the compressive strain develops. So after that, we using SWT method, which is the Gaussian equation is shown here. We used in simulation and get its fatigue life. And here it is known. Here it is found that from the middle around 20 millimeter each side, the fatigue life is very much decreased. So we can use here and many other flexible material to uh, increases performance. So the minimum value of is 9,000 cycles. After that, it will start rupturing. Thank you. Any questions you can ask me?
Yeah, if attendees have any question, they may directly ask to the presenter.
Kamalesh, this is Parasuraman here, IIT Madras. Just a quick question regarding the properties of PEK. Were they isotropic, or or are they anisotropic? Are the in plane and out of plane properties the same?
Actually, it's isotropic. We take.
It's isotropic. Oh, okay. All right. Thank you.
Yeah.
Any other question by any other attendee? So moving towards the next poster, that is poster number 88, and this poster is by Prabhasha Sharangi from LNMM School of Physical Science, Nicer, Jatni. Is the presenter here? Okay, if she is not here, then I will be just showing the poster, and whatever be the doubt or question, if the presenter want to ask, might communicate to the presenter. Her email ID should be given at the bottom of the poster. Just please have a look on the poster.
Ritesh, the presenter is just joined.
Yes, sir.
Presenter is just joined.
Sir, I'm not getting your voice clearly.
The presenter has just joined.
Sir, not audible clearly your voice. Not able to clearly listen.
The presenter has just joined. That's what he
Okay.
said.
Okay. So if the presenter want to, just what we call that, want to present, so please be hurry up and just quickly explain a poster within the 2 minutes.
Hello, sir.
Please speak loudly.
Hello.
Yeah.
Am I
Please
audible?
go forward. Yeah. Please go forward.
Okay. So here basically we have observed the spin pumping at cobalt iron boron C60 interface. So
Ritesh, can you also show us the title of the poster? So can you just scroll up? Yeah, okay.
So basically we know that organic semiconductor like C60, it has low spin orbit coupling and low hyperfine interaction and large spin diffusion length. So we have seen that if we deposit C60 on top of a ferromagnet thing, so at the interface that interface getting magnetic. So in this magnetic interface is called spin interface. Basically in the that spin pumping or spin Hall effect phenomena, it has been observed in the high spin orbit coupling material. But in C60, still it is low spin orbit coupling. Still we have seen that spin pumping thing, because this in this C60 thing, that pi d hybridization, that curvature of the C60 molecule increases the spin orbit coupling strength. So here this is our sample details. So we have basically deposited C60 on top of a silicon. We have deposited cobalt iron boron on top of a silicon substrate, and then we have deposited C60 molecule, and we have kept using MgO. And this is like in that site we have using silver paste. we have made the contact, and then using FMR we have doing the FMR and ISHE. So from the FMR also we have seen this for C60 thing, that when we have performed the single layer cobalt iron boron, we are damping for single layer cobalt iron boron, the damping is 0.0085, and wherever with that C60 thickness the damping increases. So this is also a signature of the spin pump, that signature that spin pumping is happening at the interface. And for spin hall, and also we have seen using the when we have introduced the C60 layer, using the C60 layer, that anisotropy of the system also enhanced. That reason may be because of that spin interface. And here we have performed the ISHE measurement. So this black color signal is for that FMR spectra, and this blue color is like a ISHE signal, and the, yes sir,
the video on the
and this blue color signal is that ISHE signal, and ISHE signal, it has like a symmetric part and an antisymmetric part. So this green color is that antisymmetric, and this red color is symmetric. So we have seen that this for this 0 degree and this 180 degree, the signal that signal is opposite. So this clearly tells that I say that spin pumping is happening at cobalt iron boron C60 interface. And also we have seen that at 90 degree there is like leg spin accumulation. So that's why there is no ISHE signal. So we have also performed the single layer cobalt iron boron thing, and single layer cobalt iron boron there is no ISHE signal.
And please conclude.
Okay. So here we have performed the angle dependent measurement, and from angle dependent measurement we have calculated the spin pumping, and we have seen that for spin pumping that 2.68 microvolt that spin pumping voltage is 2.68 microvolt using, and for C60 thing, when we increase the C60 thickness, that spin pumping is more. So in the conclusion, that we have seen that introducing a C60 layer, the damping increase, and also the anisotropy is increased, and we have observed that spin pumping is happening at the cobalt iron boron C60 interface. Thank you.
Session is now open for the question answer. So if anyone has any questions, please ask to the presenter.
One thing, Purvasha, why you chose this symposium for your, for your work? I mean, what it has, which sort of connection it has with flexible electronics?
Sir, actually, this symposium was like a flexible electronics and also organic semiconductor. So that's why I have chosen this one.
So, I mean, C60 is your organic semiconductor.
Yes, sir. C60 is C60 is organic molecule.
Okay. So you see a dependence on the thickness of the layer, and how you put that layer is just a coating, or how you control.
No. We have deposited C60 using thermal evaporation.
It's not a solution processed. Okay.
No. It is not. Basically, we have like powder. We have powder C60 material, and we have just heat it, and like using thermal evaporation, we have deposited the C60.
Okay. And what sort of thickness?
So for C60 thickness, like we have choose 4 nanometer C60 and also 20 nanometer C60.
Okay. And you have already explained the dependence on thickness. Okay.
Yes.
Yeah. Okay. It's fine. Okay.
Any other question? So if there is no further question, then I would like to thank the presenter for presenting the poster, and I move to the next poster. Yeah, this is the poster number 89 by Asha Kumari. Is she here online?
Yes, sir. I'm there.
Yes, sir. Yes, sir. Okay, ma'am. Then I will be giving you just 2 minutes, ma'am. Please wind up within the 2 minutes so that we should have at least 1 minute for the question answer session. So please try to wind up within the 2 minutes, ma'am.
Okay, sir. Okay. So in
Please
this work,
get
I
it.
have investigated the effect 88A3, that is the ferroelectric nanoparticle, on the polymer dispersed liquid gas based device. Uh, so the required frequency changes by changing the concentration of nanoparticle. The motivation behind this work is this, because they have application in flexible displays, projection displays, smart window, optical diffusers, and even this is a prototype of a device in which powder droplets are embedded into a solid polymer transparent matrix. So these are the liquid crystal droplets present into a transparent polymer matrix. So what happens in the absence of electric field, the effective mismatch of refractive index will be there. So the incident light will be scattered, like you can see in this figure. This is a fabricated device prepared in our laboratory. So the light scattering occur in this device, and when voltage of 20 volt peak to peak is applied, the light will be transmitted through the cell, and the thickness of the cell is only 12 micron, so the required field is very low for the doped sample that we can see here. By the doping of the B88 nanoparticle, the change in the morphology is recorded by using a POM. The change is shown over here, where the droplet size is decreased from micron to nanoscale. Typically, 15 to 20 micron in the pure case, and 1 micrometer size in the 0.58%. So this is our main target, where the transmission versus frequency curve shows that by changing the frequency of the applied frequency of the device, of the applied field, the transmission level changes from 1 to 0, and the frequency for this change is changed by addition of nanoparticles like this. This is a F10 that is required to change the 10% of transmittance, initial transmittance, and this is the 90% change in the transmittance by changing the frequency. Also, we
Ma'am,
have
please
noticed
try to
that,
conclude, Jaldi.
yes, sir. We have noticed that the rise time of the device is decreased as a result of incorporation of nanoparticles. So it dictates that the device can be used for the frequency modulation, because the initial required frequency was 1 megahertz, and for by the doping, it changes to 500 kilohertz. Thank you.
Now the attendees may ask the question to the presenters.
So hi, this is Parsuram here. Just a quick question. The barium titanate, how did you synthesize them, and what are the particle sizes?
So particles are synthesized in the chemistry department at IIT Delhi. They have used some different technique, but I have measured the particle size. The particle size is between 5 to 15 nanometer.
Oh, okay, so they're quite small then. Yeah, okay. Thank you.
Yeah.
Any other question? Okay, as there is no other further question, so I would like to thank presenter for presenting the poster. Yeah, this is poster number 91 from Akriti Singh. Is she present here?
Yes, sir.
Yeah. Just I will be giving you 2 minutes. I have to wind up within the 2 minutes. So please go forward.
Okay. I'm Akriti Singh, and going to present the work I did during my master's at IIT Delhi. So the main objective of the study was to investigate the effect of doping of magnetic nanoparticles of iron nickel oxide on a PDLC, that is polymer dispersed liquid crystal. Now, PDLC is a very important class of materials for displays, electro-optic shutters, as well as biomedical applications. They are exploited for displays as they can be switched from the off state to the on state by mere application of sufficient electric field. Now, various chemicals as well as their concentrations are listed under this experimental details, and the cells were fabricated using the temperature-induced phase separation technique, and the fabrication of such a geometric pattern was done using the positive photolithography, and the steps are mentioned here. Now, drawing your attention towards the results, so morphology was studied, and it was using the polarized optical microscope. The microstructure was analyzed using the POM, and it showed that the liquid crystal droplets have grown in number, but they have reduced in size. It was due to the higher viscosity of the doped sample. The UV visible spectroscopy showed that the offstate transmittance had decreased throughout the wavelength range from 350 to 1200 nanometers. It was due to the absorption of by the nanoparticles that were present, and it was in accordance to the Beer-Lambert's law. The electro-optic properties were studied, and the offstate transmittance had reduced drastically in case of the doped sample. This was due to the mismatch in the diffractive index of the polymer, which was containing the nanoparticles and the liquid crystal droplets. So light was scattered more, and hence the transmittance was less, and it resulted in increased contrast ratio. The switching times were also analyzed, and it was seen that the rise time as well as the decay time have reduced, and so the switching time was also improved. Now the dielectric properties were studied, and the permittivity was reduced by 10 times in case of the doped sample. This was due to the fact that the molecular interactions, these were the molecular interaction between the nanoparticles, the liquid crystal, and the polymer. They reduced the molecular order of the sample, and hence the dipole moment. So the charge carrying capacity reduced, and therefore the permittivity was decreased. Now, this study can be concluded to have increased the contrast ratio and the response time, so it can be employed for displays and as well as smart windows. However, the major drawback of this study was an increase in the threshold voltage. So the future perspective would be to employ some different weight percent of these nanoparticles so that the can be overcome to reduce the threshold voltage. Thank you.
Okay, now the window is open for the question and answer session. So any questions, please ask to the presenter. Okay, as there is no question, so I would like to thank to presenter for presenting the poster.
Ritesh, how many posters are left?
Sir, there are 8 more posters to go.
You may want to speed up because we have only around 40 minutes on the
Yeah,
clock.
sure, sir, sure, sir. Okay, sure, sir. Yeah, this is poster number 93 from Khajida Kanwal Khanum from IISc Bangalore. Is she present?
Hello.
Yeah, ma'am. Yeah, ma'am. I'm just giving you. Please be stick on the time. Actually, we are running late, So I request you to please wind within 2 minutes so that we should have at least 1 minute left for the question answer session.
Sure.
Please go for it, ma'am.
Okay. Hello, everyone. This study is to obtain different types of different topographies of flexible substrates which can be used to fabricate photovoltaic devices such as thin film, small molecule organic materials, and solution process quantum dot materials. The objective of this study was to have different topographies so that when a material is fabricated on it, we can have different topographies, and the nanofibers obtained are in the nanofibers obtained have diameter nanofibers diameter between 200 nanometer to 1300 nanometer, which is in the light absorbing range. Here you can see this has been done using single step process, that is electrospinning. And then to summarize, we have first studied 3 parameters of electrospinning, that is 3 kVs, 5 flow rates, and 5 needle diameters, and we have seen that based on this there is change in diameter of the nanofibers. Next, we have changed the needle geometry, and as you can see the SEM images in first row, we have obtained flat fibers, circular fibers, conjoint fibers, and then in second row we have obtained wrinkle fibers, porous fibers, and striated fibers. In the table you can see these fibers are made up of different polymers, and they have different nanofiber diameter, as well as they have different electrospinning conditions used for them. These flat fiber is due to PVA of needle geometry used for electrospinning is very high, therefore we obtain flat fibers, whereas conjoint fibers, as you can see the needle diameter on as an inset in SEM image, due to that we have obtained the conjoint.
Ma'am,
Porous
please
fibers.
conclude.
Okay, so here as you can see in the conclusion, we have different flexible mats. The image, the substrates we have obtained are flexible, and single electrospinning can be used to obtain flexible fiber nanomats of different topographies. Thank you.
Now the window is open for the question answer session. Any questions, please?
So, hi, this is Parthram here. Just a quick question. So what is the typical surface coverage of these electrospun layers?
The SEM images which we are seeing here is for 5-minute duration. The coverage, if we may do it for 10 minutes, as you can see the images below, it is completely, you can peel it out and you can get the flexible substrates.
Okay, thank you.
Okay, thank you.
As there is no further question, I thank the presenter to presenting the poster. Yeah, this is poster number 94 by Supriya Yadav. She is present there. Supriya, are you there? Okay, as the presenter is not there, I am just scrolling the poster. You people just have a look on it, and if any further queries will there, then you will directly write to ksupriya@gmail.com.
Please show us the live poster.
Yes, sir. It is basic.
1 second.
There is a Supriya Yadav in the room somewhere, so I don't know whether she is paying attention.
Okay.
As the presenter is not there, so if any question is there, you may directly write to her at the given ID, that is kysupriya@gmail.com. So this was poster number 94. Yeah, this is poster number 95. That is a fabrication of bender-free TiO2 nanoparticle electrodes for supercapacitor in low power electronic application by Shalu Rani. Is the presenter there?
Yes, sir.
Yes, ma'am. I am just giving you 2 minutes, ma'am. Please just try to conclude within the 2 minutes. Otherwise, actually, we are running out of time. So please try to conclude within the 2 minutes, ma'am. Please proceed.
Okay. Good evening to everyone. I am Shalu Rani. I am a research scholar from Center of Nanotechnology, IIT Roorkee. Here I am presenting fabrication of binder-free TiO2 nanoparticle electrodes for supercapacitor in low-power electronics application. The commercialization of various portable and variable microelectronic devices poses a new challenge to the various existing energy storage devices for their energy and power consumptions. And from the available energy storage devices, supercapacitor is the most promising energy storage device with a higher power density and better cyclability. Although TiO2 binder-free electrodes have been fabricated using various other techniques in the literature, but here I am presenting a simple and cost-effective electrophoretic deposition technique for the fabrication of electrodes for the supercapacitor. Here, in the experimental work, there are two electrodes. Stainless steel is used as electrode is used as a anode, and graphite is used as a cathode. These two electrodes are dipped into an electrolyte solution, which is a dispersion of TiO2 nanoparticles, and a small amount of surfactant is added to this dispersion to charge the surface of nanoparticles positively for the cathodic based EPD. Here a DC voltage is applied between anode and cathode. Under the influence of electric field, the charged particle moves towards positively charged particle moves towards the negatively charged electrode and deposit there. This shows the FSM images of the fabricated electrodes. In this experimental work, I have used two different two weight percent and 4 weight percent multivolt CNT within the dispersion of TiO2 nanoparticles. The FSM figure in the FSM images, figure A shows the FSM of 2 weight percent sample, and figure B shows the FSM of 4 weight percent sample. In the figure A, there is a multivolt CNT is forming a interconnecting network around TiO2 nanoparticles. But here, with the higher concentration of multivolt CNT shows some type of agglomeration inside the TiO2 nanoparticles. Moving towards the electrochemical characterization of these fabricated electrodes, this is the cyclic voltammetry. Cyclic voltammetry is shown at 10 millivolt per second scan rate. And this is the galvanistic charge curve at the 1 ampere per G current density.
Please
in
conclude.
the cyclic, okay. Here, with the 2 weight percent multivolt CNT within the TiO2 nano particle electrode shows the highest specific capacitance, which is 320 farad per G at 1 ampere per G current density. And by utilizing the EIS data, we have calculated the diffusion coefficient and relaxation time constant for the fabricated electrode in 2 molar KOH electrolyte solution. So the best performance electrolyte shows the higher diffusion coefficient, which is 1.45 into 10 to power minus 10 centimeter square per second, and smaller relaxation time constant, which is 89 milliseconds. And moreover, the fabricated optimized TiO2 nanoparticle electrode shows the capacity retention of 87% after 1000 discharge cycles. Thank you.
Now the window is open for the question answer session. Please, if any question is there, you may ask the presenter.
Hi, so this is Parsuram here. Just a quick question. You said you used a surfactant, right? So how do you remove the surfactant post deposition?
Sir, surfactants is not removed. It like I have used HCl as a surfactant, which and the H positive ions are attached to the at the surface of TiO2 nanoparticles and make the surface of TiO2 nanoparticles positively charged, so that it can move towards the negatively charged electrode and deposit there.
And what is the phase? Is this anatase, rutile? What is the CO2 phase?
Anatase phase.
Thank you. Yeah.
Okay.
Any other question?
Yes, so your supercapacitor measurements, they are 2 electrode or 3 electrode measurement, what you have done?
It's 3 electrode measurement system.
And what kind of reference electrode you used?
HgHg2Cl2.
Okay. So you are not seeing a very big improvement in capacity if you increase the CMT fraction. So can you explain why is that?
When because
down, so to say.
Sorry.
When you went from 2 to 4%, the capacity went down. So why is that? And then why at all you should add that CMT at all?
Yes, when we moved towards the higher current density, the specific capacitors went down because when there is an increase in the current density, the electrolytic ions do not acquire sufficient time to move towards the active electroactive site and to utilize all the electroactive site for the electrochemical reaction. That's why.
No, not that. My question was about 2% and 4% CMT.
Yes.
So when you go from 2 to 4%, your capacity is going down. So why is that?
Yes,
and if that is the case, why should you at all add CMT?
From 2% when we move towards the 2% to 4%, there is an agglomeration of multivolt CNT, and it is blocking the path for the electroactive ions to move inside the electroactive material. That's why the capacity is reduced in case of 4% multivolt CNT.
Okay. Okay, thank you.
Okay, then I would like to thank the speaker for presenting the poster. This is poster number 96 by Bhargavi T on the silver nanowire based flexible and transparent wearable electronics. So is the presenter present?
Yes, sir. Am I audible?
Please, ma'am. Yeah, you are audible. I'm just giving you 2 minutes, ma'am. Please try to wind up within the 2 minutes. It will be really nice if you will be able to wind within the 2 minutes. Ma'am, please proceed.
Sure, sir. I'm T. Bhargavi. I am a research scholar in the Department of Metallurgical Materials Engineering, IIT Madras. I'm going to present my work on variable heaters. Heaters are used in a wide range of applications such as defrosters, defoggers, in windshields and goggles, and also used in wearable devices such as smart garments and thermotherapy pads. ITO is a commercially used transparent conducting electrode, but because of its brittle nature, it limits its application to flexible devices. So, among all the materials such as other materials such as graphene, CNT, and silver nanowires, silver nanowire has been chosen as a prominent candidate because of its high electrical conductivity and flexibility. Silver nanowire has some disadvantages because of its high surface roughness and low poor adhesion to the substrate, which can be overcome by blending it with PEDOT-PSS. And the fabrication of the heater is done by printing. The PET substrate, the PET is a substrate, and the pattern has been printed on the PET substrate, and it will be annealed for 120 degrees Celsius for 1 hour. And the electrical contacts are given by using silver epoxy and copper wire. And the PTMS is used as an encapsulant to provide environmental protection and to increase the oxidation and the chemical attack. And we have also demonstrated the working of the heater by evaporation of water droplet at a low operating voltage as 3 volt. And you can also scan the QR code to view the video. So heaters basically have a should have a cyclic thermal stability. Yeah, the heaters these two graphs shows the heater as exhibits stable temperature on various heating and cooling cycles, and also under heating characteristics the second graph shows the as the voltage increases, temperature increases, which shows the thermal response of the heater to different voltages on continuous heating, and also the time taken by the temperature to reach the stable voltage. The third graph shows that the temperature increases from 41.5 volts to approximately 95.5 volts. Degrees Celsius. When the voltage is increased from 1 volt to 3 volts. Stable. So the steady state temperature was achieved within 20 seconds, which is a low response time. The low response time shows the fast response of the heater to the particular voltage, and which is the advantage of the heater. And these model shows the heat distribution of the heater at 1 volt and 3 volt, which is modeled using MATLAB and COMSOL. The conclusion.
Please conclude.
Yeah, yes, sir. My conclusion is that our heater showed a thermal cyclic stability and a low operating voltage, and can achieve a steady state temperature at low response time, which is 20 degrees Celsius. Sorry, 20 seconds. Yes, thank you.
Thank you. Now the window is open for the question and answer session. Please, if anyone has any question, please ask the presenter. Okay, as there is no question, then I would like to thank the presenter for presenting the poster.
Thank you.
This is poster number 97 by Miss Ishita Pandey from LNMM. Is she online?
Yes, sir, I'm online.
Yes, ma'am. Just I will be giving you 2 minutes to wind up. Please, ma'am, start.
Okay, sir, thank you. So, hello everyone, I am Ishita Pandey from Nizer, Bhubaneswar. The title of my talk is Strain Engineer Domain Structure and its Relaxation in a Perpendicularly Magnetized Cobalt Platinum. So, here our purpose of the work is to find out the effect of strain application on modifying magnetic properties of an out-of-plane magnetized system. In that regard, sir, am I audible?
Yeah. Please carry forward. Proceed.
Okay, so in that context, we have deposited a out-of-plane magnetized cobalt platinum film on a flexible polyimide substrate. This polyimide substrate is 25 micron thick. We have applied the strain by bending the whole film in convex and concave shape. The convex shape given tensile stress and the concave one gives compressive stress. By this one, we have studied all the magnetic measurements under Moog microscope. First, we have made the magnetic measurements in the flat state of the sample, and then we made it bend, and then again took all the magnetic measurements. So here first we have recorded hysteresis loop and corresponding domain images, and after that we have done the relaxation measurement. In the flat state of the sample, we found usual bubble domains, but under strain we found that the domain size decreases in the tensile stress. However, under compressive stress, there is no significant effect. Further, we have done the relaxation measurement on the same sample. So for that one, first we have saturated the sample in a negative saturation, then given a Z1 energy, which is 0.95 SC, and then took all the domain images by keeping the magnetic field constant there. And from that domain images, we have processed the intensity of each image and then plotted a graph between the normalized intensity and the time taken to complete the magnetization relaxation. And then the data is fitted with this compressed exponential function. By that, we have found the relaxation time obtained during the flat state and the bend state. Here we have obtained a slower relaxation in the bend state, that is the tensile one. There is a 13-second difference between the relaxation time of the flat state and the bend state. From that, we confirmed that under tensile strain, the relaxation process is very slower. Whereas in our whole work, we have not found a significant effect of applying compressive stress on the magnetic properties. So to find out that one, we have done the deposition on a different geometry, which is shown in the left-hand side bottom figure. Here, the sample is deposited on a convex polyimide substrate, and then we first measure the magnetic properties, and after that we made the sample flat, and hence in that part, compressive stress has generated on the film, and yes, sir, and a significant reduction in the coercivity has been observed. So, as a conclusion, the effect of strain on modifying the hysteresis as well as the domain images and the relaxation dynamics is significant under tensile as well as the compressive strain. Thank you.
Yeah, now the window is open for the
Yeah, so Ishita, I just wanted to ask you a few things. One is that this bending radius, how much is that? I mean, for your tensile and compressive. This is question one. Second, in the first case, when you start with a flat sample, you measure the magnetic property in the bend condition, or you bend and then again you allowed to commit to the flat condition and then measure?
Yes, sir. So, coming to the first question, the radius which we taken for the bending is varied from 40 mm to 3 mm.
Okay, so now you are
40
showing
mm
the
and 3
data
mm.
for which bending radius?
Sir, whatever data is shown here in this plot of coercivity versus strain, so there we have plotted all the results from 40 to 5 mm.
Where is that plot?
Sir, this is represented in terms of the strain. That is not in R.
Okay. Okay.
And the second one is, sir, the first we have measured the magnetic property in the flat state, then we bend it, then measured again the all properties in the bend state, and then we again made it flat and measured the same properties. So the things are reversible.
So why you see the change in the second case when you deposit on a convex substrate and then flatten it? It will be under some sort of a compressive strain then. But in first case it was again the same compressive strain, but you did not see any change. This part I did not understand. Why you did not see any change in the first case?
Sir, actually that was also our concern why we could not find that. So first case we have just bent the overall film in a concave shape, but that case we suspect that there is not significant amount of stress transfer from the mold to the film.
I don't understand. I mean, please, we don't have time, so don't just restate your statement. Just give me one line answer if you have. Why you see the change in the second case but not in the first case?
So this change is expected, but in the first case, which we did not observe any change, maybe the reason is the significant stress transfer is not happening there.
Okay. Yeah. Fine. Thank you.
Any another question? Okay, then I thanks the presenter for presenting the poster. This is poster number 98, electrodeposition of amorphous silicon at room temperature on flexible substrate by Rajendra Singh Deol. Is the presenter present online?
Yes.
Yeah, sir. Sir, please try to wind up within the 2 minutes.
Sure.
Yes. Yeah, please proceed.
Thank you, Ritesh. So this is Rajendra Singh Deol. I'm going to present on electrodeposition of amorphous silicon at room temperature on flexible substrates. So what we have tried to do is to deposit direct electrode deposition of silicon on flexible substrates such as copper foil. And we have also tried to do this same experiment on PET, which were ITO coated. And what we have done is we have used silicon tetrachloride, which was dissolved in TbACl, tetrabutyl ammonium chloride. And we also added all these things in propylene carbonate, which was the aprotic solvent. So TbACl was added to provide some more conductivity to the solution. And when we passed 20 milliampere constant current through the solution, amorphous silicon started depositing on the counter electrode surface, which was copper in this case. We have done the same deposition on ITO coated PET, which are flexible substrates, and we have demonstrated the deposition of elemental silicon on both the substrates. So the point over here is that we have demonstrated the direct electrode deposition process. When we take these electrodes out of the solvents, the silicon start to get oxidized, and we have characterized and demonstrated the percentages of silicon and oxygen present in those films. And the main idea of this direct electrode deposition is to make the silicon available for the flexible electronics and flexible substrates. And this amorphous silicon can directly be used for solar cell applications and energy harvesting applications as well. And this can be done on large scale as well. So as you can see, the XRD plot also, it also showed the demonstration of elemental silicon. And that's all, I guess, in 2 minutes.
Okay, thank you, Rajendra, for sticking to the time frame. So the window is open for the question answer session. If anyone has question, please ask the presenter.
So hi, this is Parsram here. I'm guessing these are all room temperature depositions,
Yes,
right?
yes, this is all room temperature deposition. We only provide stirring to the solution. The next step for this is to recycle the whole solution, because the byproducts used to stick in the solution. You can heat them up to crystallize your film, but the main purpose was to stick to flexible substrate and room temperature.
So what is the typical thickness obtained?
So thickness is direct functionality of your applied current and time. So what we have found out is that we can deposit up to 4 micron, and beyond that the layer started to delaminate under its weight.
Okay. Did you try to do any mobility measurements or any other electrical properties?
Not yet.
Okay. All right. Yeah. Thanks.
Hello. Yeah. Okay.
Any other question? Okay, as is there no further question, then I would like to thank the presenter for presenting the poster.
Thank you, Ritesh.
So this is the last poster, that is poster number 100, microscopic study of the gold-induced low temperature crystalline by Mohammad Shahid Irdashi. Is the presenter present online?
Yes, sir.
Okay, sir. Yeah, I'm giving just 2 minutes. You have to please wind up within that 2 minutes. So please go forward.
Yes, sir. Myself, Mohammad Shahid Idrisi, JRF in Department of Natural Science from IIIT Jabalpur. Today's my topic is microscopic study of gold-induced low temperature crystallization of silicon. In this work, ultra-thin silicon films are grown at room temperature using electron beam evaporation method on silicon and sapphire substrates. These films were studied to explore crystallization assisted by a thin AU layer, gold layer, Raman spectroscopy, optical microscopy, and cross-sectional transmission electron microscopy measurements revealed crystallization of silicon at temperature as low as 250 degrees Celsius. Under rapid thermal annealing, RT performed for only 2 minutes. Optical transmittance of silicon layers grown on surface substrates decreased with increasing annealing temperature, depicting improved structural quality for high temperature annealed thin films. Here are the result and discussions. In figures, we have see the layer structure of the grown amorphous silicon thin films. So the optical micrograph of silicon gold silicon tri-layer stack grown on silicon 100 and sapphire 0001 substrates. The images for as grown samples show presence of a smooth surface having no distinct features. With annealing, silicon grains start to form. The grains increase in size till an annealing temperature of 400 degrees Celsius on sapphire substrate, after which a reduction in grain size was observed. Average grain size was found to be nearly 3.5 micrometer, 30 micrometer, 20 micrometer, and 12 micrometer for annealing temperature of 250 degrees Celsius, 400 degrees Celsius, 600 degrees Celsius, and 800 degrees Celsius. Respectively, the reason for the size reduction, higher temperature could be impacting under crystallization or fragmentation of grains. The grains on silicon substrate showed a monotonous increase in size up to 800 degrees Celsius. Presence of crystalline silicon in the brighter parts of the images shown in figure 1 was confirmed using Raman spectroscopy. Figure 2 shows micro-Raman spectra of the thin films observed in the brighter and dark regions as seen in figure 1. The spectrum taken in the bright regions contains a peak at 520 per centimeter, which correspond to optical phonon mode of silicon. Raman peaks that are visible near 417 and 750 per centimeter correspond to Raman active modes of sapphire. Raman spectrum observed in the dark regions shows only sapphire-related peaks and thereby confirm the absence of crystalline silicon in the dark regions. In figure 3, Raman spectra of the as deposited as well as annealed samples, the intensity of longitudinal optical Raman mode of crystalline silicon increased with increasing rapid thermal annealing temperature, signifying an increasing fraction of crystalline silicon in the samples. In figure 4, sardine and
Yeah, Mohammed Shah, are you there?
yes sir, yes sir.
Yeah, please just try to conclude. We are running out of time. Please conclude within half a minute, please.
Yes. Induced crystallization has been observed in a layer stacked silicon 10 nanometer, gold 5 nanometer, silicon 20 nanometer under rapid thermal annealing temperature at temperature as low as 250 degrees Celsius and an annealing duration of only 2 minutes. Optical microscopy showed the formation of crystalline silicon grains with dimension of microns as shown by XTM measurement. Silicon can perfectly crystalline in these grains and may be useful in devices that can be grown on a few micron grains of ultra-thin crystalline silicon. Thank you, sir.
Okay. Now the window is open for the question and answer session. Please. Any questions? Okay, as there is no further question, so I would like to thank to the speaker. With this, we come to and
Thanks,
with this we
Rite.
come to. Yes, sir. Please, please, sir. Please.
Yeah, so I would like to thank everyone who participated in the poster session. This is a slightly awkward type of interface where the freedom to move around and look at interesting features of different posters is not available to us, but such are the times we live in. Thank you all for coming and for presenting your work. And we will be now moving to Hall 8 for the last remaining engagement of the day for the symposium, which is a talk by Professor Guo, and I'll see you there in a few moments. Thank you.
Hello, Ankur.
Hello,
Hello.
can all hear me? Hear me?
Yeah, Ankur, I can hear you.
Uh, go coming. Is my voice clear or is it feedback?
Your voice is clear.
Okay. So we can start by another 5 minutes or so. There's a posters are going on in the other halls. So maybe another 5 minutes more.
But is this the right link? I just heard
This
Madhusudan
is
announce that this session is over and now there's some other
this
talk
is
which.
this is the hall 3 for your talk actually. That is for the other. So there are parallel sessions are going on, right? So this is the hall 3 for the your talk actually. We have couple of talks from 5 to 6.
So what
So
was this announcement that this session is over and there's another talk in
no,
some.
that is the poster session is over because there are parallel poster sessions are going on in different halls. So the 2D materials was going on in hall 2 basically. I am not sure whether you are aware of that because I was in that hall, but the talk will be here. So here, this was the posters which was going on of, let me see. So there are some other poster sessions were going on, which Madhusudan was a convener of that session.
Oh, so that was not the 2D material session.
No. So the
Okay,
posters was
okay.
distributed in different halls. So I'm not sure whether you got the. I thought I was in a notion that everybody has got the link for the poster. So I was a judge in the hall 2 for 2D materials and devices. But here
No,
Madhusudan
no.
was okay. You have not got the link. Okay. But anyway, the interface. Yeah.
Somehow
Please
I
go ahead.
thought that these are posters which the 2D materials session received, and I was kind of surprised.
No. So I think there is a bit miscommunication from our end, because this is also a different interface, and that is happening, that we are also some way swapping in between every halls. So there are 4-5 judges on the hall 4. I was in a notion that you got the link. So, but extremely sorry for that. Maybe we'll try to convey
No
this.
problem.
Okay. So we can wait for another 2 minutes and we can start.
Yeah.
Okay.
Do you have enough
I
audience here? I mean, how many people are attending?
They will join actually.
The
Yeah.
participants that I see here, that's the only audience that you have, right?
Yeah, but some more will join because the poster sessions are going on, right? So you can expect another 2-3 minutes they will come here. So that's what I'm waiting for.
Okay.
So
And the poster
mostly
session
we
is still
have,
running.
yeah. So mostly we have normally 22 to 25 audience in every sessions. That what I have been observing from the morning from each symposium. So you can expect that kind of audience or more. So I believe they will turn up.
Hello, can you hear me?
Yes.
So we are about to start this session, next session. Welcome all of you for this today's last session for these 2D materials and devices. And this session, the Professor Ankur Goswami will be chairing this session. He is attached to the Material Science Department at IIT Delhi. He works on MEMS and other materials and 2D materials and their device applications. So I'm not wasting time because it's already more than 5. So now I am thankful to Professor Ankur Goswami for chairing this session. Now I give it to you, Professor Ankur Goswami.
Okay, thanks, Amadesh. So with that, we will start our session, this particular session. So now Professor Mayank Srivastav is going to give a talk. We have two talks, consecutive talk. One is first is invited talk from Professor Mayank by Professor Mayank Srivastav, IIC Bangalore, and then Mrs. Neha Sinha from CNN Punjab. So let me introduce Professor Mayank Srivastav. His title of the talk is Defect-Assisted Atomic Orbital Overlap Engineering in Graphene and 2D TMDs, resulting in record high-performance transistors. His brief CV, I'd like to say he has done PhD from IIT Bombay. He received Excellence Research Award in his PhD thesis. He has a lot of Industrial Impact Award from IIT Bombay in 2010. He is in IIC Bangalore as a associate, as a professor. He is among the first recipient of Indian section of American TR35 award and the first Indian to receive IEEE EDS Early Career Award. Besides that, he is IEEE senior member and has received several other national awards, honors, high repute like National Academy of Science. So with that, he has a very illustrated background in research. So I'm not going to go into the details of all, but I will ask Professor Mayank Srivastav to take it over and then present his talk. So let us listen to him. Okay. Over to you, Professor Srivastav.
Thank you, Professor Samresh, Professor Ankur, for inviting me here, as well as for the nice introduction. So in next 30 minutes, I'm going to talk about how we, try to understand some of the fundamental or quantum chemistry behavior at metal and 2D material interfaces. Here, in terms of 2D material, I'm talking about graphene as well as several transition metal dichalcogenides, and how understanding, some of these fundamental behaviors helped us engineering the device and reporting record high performances, both in terms of contact resistance as well as transistor performance. So let's begin. This is the outline of my talk. I'll quickly tell you, what graphene and 2D materials are, their properties as well as the applications. I'll try to help you understand why contacts are so important, particularly for these technologies. What is the state of the art? I'll tell you what we already know. I'll briefly touch base on the quantum chemistry of contacts. And then using this understanding, how do we improve or the engineer contacts? And then finally, I'll show you the technology that we developed with record low contact resistance and record high performances. And then I'll summarize my talk. So graphene, most of you would know that graphene is one atom thick, hexagonally arranged lattice of carbon atom, where each atom has 4 bonds. One pi bond and 3 sp2 bonds. So you have in-plane sigma bond and out-plane pi bond. Out-plane pi bond is responsible for the conductivity, and the in-plane sigma bond is responsible for the thermal properties and the strength of the material. As far as the band structure is concerned, somebody muted me. So graphene has 2-dimensional Dirac cones, and here the electrons obey 2-dimensional quantum electrodynamics. This is little different than what happens in bulk semiconductors, and so here the particles are treated as massless Dirac fermions. So these are ultra slow relativistic electrons. The Fermi velocity is very high, and that's 1 by 300 times of the speed of light. A lot of fundamental work happened in this close to 15 years back, understanding how graphene behaves. As far as the 2D materials are concerned, there's a broad, wide family of 2D materials. They are xenenes, in which you have graphene, silicene, germanium, phosphorine, and so on. You have xenanes. Then you have transition metal dichalcogonides. That's another interest of my group, where we work on moly and tungsten-based diselenides and sulfides. And then there are many other materials. I mean, if you look into the whole family, there are more than 700 2D materials, which has been predicted to be stable so far. Now, depending on how they bond or how the phase is arranged, they may have different properties. So depending on whether they have a 2H phase or 1T phase, they may be semiconducting or metallic. Here we are talking about mostly semiconducting TMDs, where which you will use for transistor applications, and where the contact becomes interesting problem. They're also interesting, and some of these problems are also important for optoelectronic applications, and that's also the reason why you want to address some of these issues. Right. As far as the graphene is concerned, graphene offers highest channel mobility, 1,000 times higher than silicon. It has 4 to 5 times higher saturation velocity than silicon, and it has a much longer mean free path or scattering length compared to any other bulk semiconductor material, and that's one of the reasons why it offers or it is quite a promising material for transistor and many other applications. For instance, you can think of transistor scaling, you can think of making terahertz kind of technologies, which is not possible with conventional materials. Graphene, for instance, can go theoretically up to 20 terahertz. Or even if you look into the properties from the metallic point of view, or from the applications as metal point of view, it offers much better performance than copper, and that's the reason why you can think of graphene as a better material in all aspects. As far as the applications are concerned, other than transistors or optoelectronic, there are many other applications where you can use graphene, and contacts are important for everything. As for the 2D materials are concerned, 2D materials have the smallest lambda, which is the parameter defining how much you can scale the transistor, and it also has the highest immunity against short channel effects compared to any other bulk semiconductor. And that's the reason why it is projected that if something has to happen down to 1 nanometer dimensions, it can happen only with 2D materials or these kind of transition metal dichalcogonides. Worldwide, there's a lot of effort going on 2D transition metal dichalcogonides, including recently demonstrated growth, large area growth on 300 millimeter wafers, and device fabrication on 300 millimeter wafers by IMEC. There are many other possibilities that you can think of doing with 2D materials. You can think of 2D materials having applications in brain computation. So my group works on neuromorphic hardware and memories as well. You can think of using 2D materials because they are pretty much massless. You can think of doing lightweight electronics or bioimplantable or wearable electronics, and you can also think of high performance electronics or high performance flexible electronics. And more recently, they are also being demonstrated to be used for quantum communication and quantum computing devices. That's why the 2D material has a lot of there's a lot of interest in 2D materials, and the reason why there are a lot of major programs around the world with investment of more than $1 billion. Now, from the transistor performance point of view, if you look into the cutoff frequency question, which makes it quite obvious that why contacts are important. If you reduce these series source and drain resistance, you can significantly gain on the cutoff frequency, which is the maximum frequency at which the transistor will behave like a transistor. So that's one of the reasons why you want to improve the contact resistance. The other reasons are, if you don't have reasonably low contact resistance, you are going to compromise in terms of the saturation characteristic of the transistor, as well as the drive current or drive capability of the transistor. In terms of graphene, theoretically, it has been projected to achieve 20 terahertz. However, the experimental, which is only one data point, is close to 400 gigahertz. And there's a big gap. Contacts have been one of the key reasons behind this gap. Okay, so let's see what we already know as far as if you think of contacts just from the fundamental quantum mechanical point of view, without bothering about which material we are talking about, there's a fundamental limit defined from the principles of quantum mechanics. Now, if you calculate based on these numbers, it would appear that the metal and TMD contact resistance would be way high than what you can basically achieve with with silicon today, or even what one can achieve with graphene today. Now, our problem statement was, can we break this fundamental limit? And can we demonstrate something which is lower than what one could have demonstrated, or one has demonstrated with silicon, or one has projected with, let's say, other kind of bulk semiconductor materials. As far as the graphene metal contacts are considered, the entire work in the literature is distributed into 3 different phases. In the very beginning, people used to do a lot of process optimizations to see if the process is the bottleneck for the contacts. For instance, there were reports in terms of rapid thermal anneal, substrate passivations, plasma heating, photoresist-free interfaces, or other kind of cleaning methods, which certainly improved the contact resistance, but the contact resistance were always in the range of few kilo ohm micrometer. Then people tried developing the semi-classical picture using the fundamental understanding of metal semiconductor interface, and using that, people concluded that you cannot achieve anything lower than 160 ohm micrometer. However, we questioned this, and we felt that why the Schottky barrier theory fails in case of graphene, because as per the Schottky barrier theory, if you scale the if you reduce the temperature, the contact resistance should increase. However, in case of graphene, if you reduce the temperature, the contact resistance reduces. Then was the time when we also started exploring the quantum chemistry of graphene and metal interfaces, and there are a couple of works. And what we found was, you need to basically think about the hybridization between the metal, the orbitals from the metal atoms, and the orbitals from the carbon atom in graphene. And therefore, it becomes very important to decide which metal to choose. You cannot choose the metal based on the Schottky barrier theory, where you decide based on the work function of the metal. You have to think about the energy orbital, and the number of filled state, the number of empty states, and and which orbital under which state will hybridize in the best way with the carbon atom in graphene. And again, you have to do some engineering with the carbon atom in graphene to make the hybridization to make the hybridization take place. There are also some other reports which demonstrated lower contact resistance of the order of 200 ohm micrometer. Mostly some method of realizing a 1D contact. However, none of the reports demonstrated or discussed the quantum chemistry behind the said improvement in the contact resistance. As for the TMD metal contacts are concerned, this is rather recent compared to graphene literature. So for instance, people tried doping the TMD, so there are different dry methods having the classical thinking. People tried doping the TMD metal interface. People tried interfacing graphene between the TMD and the metal. People tried making transferred contacts, which means that you are trying to make contacts without damaging the TMD layer. Or doping by, for instance, phosphorus implants, low energy phosphorus implants, or other kind of interface engineering to get rid of Fermi level pinning. However, in most of the cases, the contact resistance reported was always higher than 1 kilo micrometer. However, our target, if you want to get something as good as silicon, is of the order of 100 ohm micrometer or below. There are also several wet processes which people demonstrated, trying to do a charge transfer doping based on wet processes. However, the problem with these methods is that the moment you do the next level cleaning, like DI water cleaning in the process, the doping is gone. So this is a summary of the state of the art which was demonstrated before our work. So as far as the CVD graphenes are concerned, the best numbers were 200 ohm micrometer, and I must highlight that these numbers were demonstrated at low temperature, mostly around 4 Kelvin temperature. The moment you increase the temperature, the numbers will shoot around 400 to 500 ohm micrometer. The same was getting better with silicon carbide grown, epitaxial grown graphene on silicon carbide wafers. Again, at low temperatures, the moment you increase the temperature, bring it to room temperature, you see something like 300, 400 ohm micrometers. So we tried understanding, what really causes this kind of contact resistance, and we did several investigations. I'll just try to summarize that in 2 slides. So, for instance, what we found is that from atomistic computations, that the current contribution from the edge is 40% higher from rest of the overlap region, which means there is something different happening at the edge compared to the overlap region. What we found was that in the overlap region there is no bond formation. There is only van der Waals force of attraction, and therefore that's the tunneling contact. However, in the edge region you have carbon atoms which are not completely satisfied, and this forms the bonding channel. These are all sp hybridized carbon atoms, And so therefore these sp hybridized carbon atoms are able to hybridize further with the metal atom. In that case it was palladium. Again, you have to decide you have to choose the right metal for the right hybridization to take place. So we investigated various metals, and I'm showing you results from 2 different metals. And what you see is that if you use palladium over platinum, which from the conventional work function based theory, they should behave same, but in this case palladium hybridizes better with sp bonded sites, and therefore you have a better charge transfer at the edge region, whereas there's more or less similar charge transfer in the overlap and the channel region. In the TMD metal contacts, what we found is we investigated the interface, the TMD metal interface for various different TMDs and various different metals. And what we found is that the transmission probability is poor if you have a defect-free contact. However, the moment you introduce a sulfur, interstitial, or a sulfur vacancy, your transmission probability across the interface improves, which means you have to think of introducing a sulfur interstitial. In general, what we found, if you introduce a chalcogen interstitial in case of a TMD metal interface, your transmission probability will improve. I'll show you later how experimentally we introduce these interstitials, or how we introduce these sp bonded sites in case of experiments. So what you see here is again the TMD metal contacts, and we experimented various different metals under various scenarios. These are all quantum simulations, and it shows that the moment you have these interstitials introduced along with metal, there's metal induced gap states created. If you don't have metal, these gap states will not be created, and if you don't have these gap states, you cannot introduce these tunneling channels through which you can improve the contact resistance. I'll skip some of these things in interest of time, and I'll quickly jump on the engineering part. So, as far as the sp bonded sites in graphene is concerned, what you can do is you can either knock out some of the carbon atoms, and you can create these unbonded sites in the contact area, or you can also pattern the contact area in these kind of nice strips and achieve these sp bonded sites. So we further investigated, and we found from quantum simulations that the moment you introduce these kind of defects, you significantly improve the density of a state over there, as well as the transmission probability. So we introduced various methods. For instance, we used electron beam, the high energy electron gun inside the electron beam lithography tool to write down these regions where we can burn graphene locally inside the contact area. We also used argon and oxygen plasma to basically knock out carbon atoms from the contact region. What you see here is this pink region is the mask, and the open region is the contact region. We also patterned the contacts, as you can see here, to introduce more and more sp bonded sites. So finally, we developed this. A lot of work also went in improving the process recipe and other things. And this is the typical TLM patch that we achieve. So for instance, what you see here are these patterned regions inside the contact, where the edges of these blue regions will give you additional sp bonded sites, right? So then when you see, if you measure, if you do Raman scan and measure the defect density as a function of the exposure time under oxygen or argon plasma, what you see is that as you increase the exposure under the plasma, the defect density increases. That confirms our hypothesis that we are using the right process. As far as the TMD metal contacts are concerned, what we did, we basically introduced, we developed a wet chemistry to introduce these sulfur interstitials. So what we did, we basically exposed the material at high temperature under H2S. H2S is the same gas which is used for growing these materials in the same growth chamber. And but at moderate temperatures, when they come in presence of TMD, they will break. The hydrogen will dissipate out, and the sulfur or the selenium will bond at the sulfur side. And then you deposit metal on top of that. So that's how you can introduce these interstitials between the metal and the TMD below that. So as far as the graphene is concerned and these transistors are concerned, of course, we worked on various other process improvements as well. For instance, transfer process, improving the mobility while transferring the material and patterning them, gate oxide reliability, gate stack, and so on and so forth, right? And eventually we develop this long 7-mask process. As you can see, these transistors. I'll come to the results finally. So, what you see here is the contact resistance in case of graphene. And as we increase the plasma exposure time, which means we are increasing the defect density inside the contact region, you see there's an optimum point, optimum exposure time, or optimum defect density when you have the least contact resistance. This is less than 100 ohm micrometer. The similar things we achieved in other methods as well. So previous was the some material. This is with oxygen plasma with CVD graphene. Then we also demonstrated the same with argon based exposure, and then we have regions where we patterned. We have process where we patterned regions inside the contact. And then, along with this patterning, we also introduce defects. So in case of the situation when we have patterned contacts as well as defects, we achieved the lowest contact resistance. So in this case, this is 84 ohm micrometer, right? You can use argon plasma as well for slow kind of defect creation and as a fine tuning measure. So if you compare the contact resistance for different kind of methods, this is the intrinsic, which is giving you very high contact resistance versus the other methods that we use, the argon bombardment, electron beam, oxygen bombardment, the other electron beam process, oxygen plasma, and other kind of contact engineering. You see the contact resistance always fall in the range of 100 ohm micrometer. So let me summarize the graphene metal part. What we notice that there is an optimum SP defect density that you need, and that's why you see this V-shaped kind of characteristic. We have for the lower defect density regions, you have the contact dominated by tunneling, not bonding channel. If you have very high defect density, you will have current crowding in the overlap region. You have poor contacts. When you have very high contact resistances, the gate dependence was higher. However, when you go to lower contact resistance, the contact resistance was not at all dependent on the gate bias. And that's exactly what you need for the right contacts. And the contact resistance without defect engineering, in case of exfoliated, it is 3 times lower than CVD. However, when you have contact resistance with defect engineering, the exfoliated and the CVD contact resistance fall in the same range, and that is the record low number. And I must highlight that the numbers that I demonstrated, they are all room temperatures number, not low temperature numbers. The other thing is that, so once you have the optimum contacts, it offers the least variation. So there's no variation in the contact resistance from one die to the other die. You can use argon plasma on top of oxygen plasma that can be used to fine tuning the required defect density. For least contact resistance, not a significant difference was seen between contact resistance reported at 100 Kelvin versus 300 Kelvin. So finally, the electron beam based patterning or oxygen plasma based defect creation offers the least contact resistance. So this is the summary chart that you see compared to rest of the literature, and this is where the numbers are. The recent results that we have are much better, of course, but still these are all record low contact resistance numbers. Well, I must say that these are all record low contact resistance numbers measured at room temperature and measured using DC measurements, but there is a fundamental limit or fundamental to the intrinsic contact resistance, and for that we also investigated these contact resistance at nanosecond time scales at very low temperatures. And as you see that when you basically measure the contact resistance with much shorter electrical impulses, the contact resistance falls significantly. So what I'm trying to claim here is that these numbers are high in because of DC measurement, which will introduce a certain self-heating. But the moment you do the measurements with pulse setup going down to nanosecond time scales, you get these numbers to be much smaller and getting to the fundamental limits of these contact resistance. Now, as a function of the contact resistance, what we see that you also get the mobility. These are all high field mobilities. You see that the mobility also improves significantly. So the lowest contact resistance lot will give you the highest mobility. No matter which method for contact engineering you deploy. Then when you reduce the contact resistance, what we see, as I had shown, that the mobility improves significantly. We get to 6,000, 7,000 centimeter square volt second. High field mobility. The high field mobility is not something which typically people report. People often report Dirac mobility, which will be in several 10,000. But the moment you measure high field mobility, you will not get even 1,000. So what you are getting here is a high field mobility, and the transistor performance is decided by the high field mobility, not the Dirac mobility. Then we also notice that the transfer length, scales down significantly as the contact resistance scales, which means that you can make these contacts much shorter than what often people do in experiments. The mobility roll-off as a function of channel length scaling was also significantly improved when you improve the contact resistance. And as you can see that the on current also improves significantly as a function of channel length. When you have lower contact resistance, in case of higher contact resistance, this kind of channel length scaling is often not seen. That's what you see here, that as we scale the contact resistance, we can get to the intrinsic drive strength of these transistors, and not a significant difference between low temperature performance versus room temperature performance. Mostly the ion by I Dirac was also improved significantly. We got to around 5, which is again record high. Often because of poor contact resistances, you will not see very high ion by I Dirac, which you see here, that this is the standard device without contact resistance engineering. You don't see much of a difference between the Dirac current versus the maximum on current. However, when you have these contact engineered devices, you see very nice textbook-like characteristic because of missing doping from the contact into the channel. You see very high drive current ability for these contact engineered devices, very high transconductance and mobility improvement for these contact engineered devices. And this is a comparison with the best reported number. The best reported number was by IBM TJ Watson lab, and what we demonstrate is 20% better performance compared to the IBM's work. I must highlight that IBM's work was using epitaxial grown graphene on silicon carbide, which is intrinsically expected to offer you much better performance compared to what we did, which is silicon oxide dielectric and a CVD graphene. Now switching gears to TMD transistor performance. As you see with the contact engineering that we deployed, the transistor performance of the engineered devices, which are in white color, are significantly better compared to those which are non-engineered, which are in the yellow color here, or in different colors in the different charts. Those which are engineered are always in the white color in the first row, or with the green color in the second row. So as you can see that no matter which metal you deploy, of course you need to choose the right metal for the right TMD, but no matter which TMD you use, if we have this kind of contact engineering that I demonstrated earlier using this sulfur interstitial, which is a dry process that we developed, you get significant improvement in the transistor performance in all the aspects, whether it is ion by I off, contact resistance, threshold voltage shift, and so on, which I have compared here. So if you see the transconductance, depending on which material I talk about, the transconductance improves from 2 times to 20 times. The I of the leakage reduces by 3 orders of magnitude. The ion by I of improves by 4 orders of magnitude. Mobility improves by 2 orders of magnitude. Subthreshold slope improves by 2 to 3 times, and the contact resistance improves by few times to 100 times. We also transferred this on a CVD material, and the same performance improvement can be seen on a CVD MOS2 device as well. So what you see here is the contact resistance measurement. We're using Y-function method, and the devices without engineering will give you contact resistance of the order of 5 to 10 kilo ohm micrometer, which is the typical number which often people get. And what we are getting after the contact resistance engineering is around 50 to 100 ohm micrometer, which is record low contact resistance for these kind of materials. With this contact resistance engineering, we could also demonstrate, p-channel transistors, which is something which was found to be fundamentally very difficult in these kind of materials. So what you see here is that, depending on which metal you choose and the kind of metal induced gap state engineering that we do, we can either get an N channel operation or a P channel operation. In this case, this was a tungsten diselenide TMD. So what you see here is that these are all N channel devices and these are all P channel devices. If you see here, these are all N channel operations and these are all P channel operations. So using the same TMD material, depending on which contact you choose and what kind of contact engineering we deploy, you can get N-type material or N-type transistor or the P-type transistor, thereby enabling a CMOS operation in these kind of devices. So finally, let me summarize. I talked about role of sp hybridized sites in case of graphene. I talked about orbital overlap engineering can significantly lower the contact resistance. I talked about variety of techniques to engineer orbital overlap and therefore the contacts. The devices with engineered contacts were found to offer scalability, much better scalability without sacrificing the channel properties. As we see the performance, we could achieve the performance close to its intrinsic limits, 6 times improvement in drive current, 8 times improvement in transconductance, and 6 times improvement in the mobility. As far as the technology is concerned, at room temperature using CVD graphene, we demonstrated contact resistance, which is 84 ohm micrometer, which is 138% lower compared to any reported number with CVD material and 28% lower than epitaxial material. As far as the transistor performance is concerned, we demonstrated 20% better performance when compared to the best reported number that was demonstrated for graphene on silicon carbide substrate. As for the TMD metal interface is concerned, I discussed about the role of S interstitials and selected metal atoms. So the metal-induced gap states and defect-induced gap states to engineer the orbital overlap was discussed, and therefore the contacts can be discussed with this. Devices which were engineered in the contact area with these kind of methods offer much better scalability without compromising with the channel property. And these engineered devices, were found to offer improved performance in all aspects, which are short channel effect, getting the threshold voltage shifted to positive, which was also a fundamental issue often seen in these TMD materials, lower leakage, improved short channel effects, improved drive current, as well as getting a PMOS operation. So as for the technology front is concerned, we demonstrated record high performance at 300 Kelvin, which is room temperature. We demonstrated contact resistance as low as 58 ohm micrometer, which is 400% better than any number reported till date. We demonstrated transistor performance, which is in terms of overall performance, there was a performance boost. And that is something which was never shown before. If you see somebody is reporting contact resistance improvement, often they would compromise in terms of the short channel behavior or the leakage behavior, or most of the time their transistor will become so leaky that it's no more a transistor, it's just a resistor. However, in this case, what you saw that we have an overall performance boost, not only the contact. And using this engineering method, we are also able to demonstrate or make p-channel transistors with record high performance. And these will eventually enable TMD-based CMOS features. With this, thank you very much, and I am open to any question.
Thank you, Professor Mayank. Now it is open for discussion. So if you have any question, please ask.
So can I ask a question? So this is Samresh. So very nice talk, Professor Mayank. So and a good overview for the contact, how contact play has an important role for these 2D materials devices performance. Just I want to know, like in the last section, you shown like this same TMD showing P-type and N-type behavior by just changing the contact. So is that when you do the metallization, some diffusion is happening, or why it makes what is the origin of this P-channel and N-channel behavior?
Okay. That's a good question. I did not cover this here. There's a separate paper on that. So what you see here is, let's say you have a TMD. In this case, this is tungsten diselenide. And what you see, if you want a P-channel device, what I have listed, you need chrome. And if it is N-channel device, what I have listed, this is nickel. Okay. And then we also have these interstitials. As you see, these atoms which are drawn here, these are sulfur interstitials. Now, what happens is that these metal atoms, depending on which metal you choose, together with these interstitials and TMD will do a certain modification with the gap states, with the band structure in that particular region. So what we found, if you use a certain kind of metal, let's say chrome or similar metals, metals having similar kind of orbitals, will basically form gap states, which will enhance the whole injection across the TMD. We are not doping anything, right? And if you use nickel, they will introduce certain different kind of gap states, which will enhance the electron conduction across the channel. So the material is intrinsic. The material can conduct both electron and holes. That's what we found. All you have to do is you have to allow the electrons or holes selectively to get injected. So if you do the contacts in this fashion, with the kind of engineering that I have talked about, using these interstitials, if you're using one kind of metal, which is chrome, which is the gate metal for NMOS, and if you're using nickel, which is the gate metal for PMOS and contact metal for NMOS, you can get hole injection or electron injection in a selective fashion. So our process is following that. Chrome is used as the source drain metal for P-channel transistor and a gate metal for N-channel transistor, and nickel is used as a source drain metal for N-channel transistor and gate metal for P-channel transistor. That's how we have this kind of nice self-aligned symmetric process. And selectively you get electron injection in one case and the hole injection in the other case.
Okay. So these states are creating inside the band gap of the
right. These are mid-gap states. So these are basically created between the band gap. So in one case, they will be, you have donor-like states. In the other case, you have acceptor-like states. So again, depending on how they align with the metal work function, in one case, you will have electron injection enhancement. And in the other case, you will have hole injection enhancement.
Okay, thank you.
Hi,
Any other question?
Yes, I have one question.
Please go ahead.
So in the graphene case, how defect states defy the Schottky barrier height theory? Like you told, it will give the other way Schottky barrier height at that.
There is no Schottky barrier height in case of graphene.
Yes, sir. So, so in TMD, we have Schottky barrier height with the contact, and so that how you can interlayer between the metal and the graphene, how that play into the picture? Like if you say in some reports, some have reported like this nickel or chrome or aluminum also make some oxides during the fabrication or some chemical change.
I'm not sure if I got your question.
So I want to know about the interlayer effect with the metal and the graphene during the fabrication. Like some reports have shown this metal during the metallization also form some oxides.
Mm-hmm.
So do you have taken that into account also during these studies? Or?
Account means these are all experimental works. So
yes, sir.
Yeah, so if there is an oxide formed, that is formed, and what we ensure in our process that there's no oxide formed. And that will happen if you're using aluminium, of course, but not with these kind of metals. And of course, when we do all these processes, these are all ultra high vacuum processes. The interfaces are highly cleaned. I mean, there's a lot of optimization which go into that, but once you have done that, there's no oxide at the interface.
Okay. And so the second question is, what is the degree of controllability during the patterning of specific patterning of graphene you shown in the initial slides?
Yeah, we are processing a lot every week, and every lot will have close to 500 to 1,000 devices, and out of those 1,000 devices, 95% will work. So we have pretty good controllability. Again, that's a lot of optimization you have to put in to basically develop a process for defect-free and PR residue-free graphene patterning.
Okay. And last question in TMD is there some way to keep in check these gap states? So you mentioned in chrome and nickel. So with sulfur, you mentioned the gap states are playing into the picture for N-type and P-type behavior.
You mean to say, is there a way by which you can probe them?
Yes, specifically if we can keep in check, like if we want to have some higher value or some lower value of RC, so with the help of tuning the gap states by some way, some mechanical or electrical way.
No, you can do XPS. I mean, we have done some XPS measurements in our work where we have shown, if you read this paper, this paper has a lot of Raman PL XPS investigations, which will talk about, all kind of things. You can do certain things from Raman, certain things from PL, certain things from XPS in terms of the Fermi level shift and so on. We are also investigating some of these things with STM. In case we can show that there's difference in the electron population or electron cloud depending on wherever we have these gap states introduced. So yeah, I mean, you have to think of innovative ways of probing these kind of things because these are not like conventional semiconductors.
Okay, thank you.
Okay, if there is no more question, I have a quick question, Professor Mayank. It's a very nice talk. That question may be weird, but I thought of asking that in 2D materials, if you use graphene as a contact, do you think any improvisation can happen in terms of your contact resistance, or any thoughts on that direction using graphene as a?
We tried that. That's
Okay.
not straightforward.
Yeah, I understand.
I think there is only one paper where people demonstrated if you insert graphene, there is a reduction in the contact resistance. But many of these initial reports are a little misguided in terms of the relative improvements. I mean, yeah, they bring some insights, but in terms of relative improvement, in the initial days, the contact resistance numbers were like several 10,000 kilo ohms. Now, if somebody demonstrate from, let's say, 20,000 kilo ohm down to 10,000 kilo ohm, claims that as an improvement, but we are talking about numbers of the order of 50 ohm micrometers. Right. So even if you insert graphene first, the process is challenging. That's not a scalable process. Now the runs that we do in each die, we make around 500 to 1,000 devices. You can't do that with this graphene sandwiched in that region, where you have to exfoliate graphene and put it there. You can't do that with 1,000 devices or with a very large chip. Second is that the kind of improvement you get will, in terms of absolute numbers, it won't be of any use. You may get some percentage improvement, but in terms of absolute numbers, that's of no use. So when we talk about these kind of engineerings and improvements, you have to also get to the absolute numbers desired for these kind of technologies.
Okay. Okay, thanks a lot, Professor Mayank. And with that, I think we end his talk. And the next talk will go to Ms. Sneha Sinha. I hope she is around. Or... Oh. Okay, I don't see she's here. So if not there, if you have some more question to Professor Mayank, you can ask. We can continue the discussion, and otherwise we can leave from here. We have a nice talk. Professor Venkatesan is going to give a talk on plenary lecture in that will be at 6 o'clock. So that is open to all, and yeah, I think you all got the link for that.
Yeah. So Ankur, once finish, then we have an announcement.
Okay. Okay. Please go ahead.
No question.
Yeah.
We are thankful to Professor Goswami as well as Professor Mayank for giving a very nice overview about the 2D materials devices mainly, because a lot of people talk about the 2D materials, synthesis, all these things, but device making is really hard job, and he has shown very high mobility by tuning proper contact of the devices. So nice talk. So thank you, Professor Mark. Now there is a small announcement because some of the poster presenter did not have the chance to present the poster. So for the 2D materials and devices, rest of the poster will be presented tomorrow in Hall 8. So please join Hall 8 for during the poster presentation for 2D materials and devices remaining poster. I think 10 poster remains, 10 or 12 something. So thanks, sir. Thank you. That's all for me, Professor Goswami. Hello, Ankur, can you hear me? You are muted.
So we can leave now, right? We are
Yeah.
done in this. Yeah. Okay. Thanks a lot to all.
Thank you all.
Yeah.